Es que tengo una lectura, ¿no? Está todo de verdad. Lo de sonoro la voy a poner. No sé lo que diga. ¿Cómo? Sí, me quedo trabajando. Ahora mismo la soy de cátedra, pero claro, tiene que llegar a un más lector.
Tenemos ahorita un grupo reducido.
Y a Dani le baila y con
David y Mauro están haciendo.
no sé.
Okay, so we will start the afternoon session, the last talk. But before that, we have an announcement. We will take the picture. One picture at 6.
Okay.
Before.
Okay.
Where?
In the fountain.
Downstairs.
Downstairs by the fountain with the
So the next talk will be given by Carlos Vaquera from Guanajuato. And he will talk about beyond 331 models.
Thank you. The good place. Thanks for the invitation. I love to come here. And I will talk about this class of models, 331 models, which are one of the least popular extensions of the standard model. But I will try to convince you that this class of models and their extensions are worthful. So I will start with a little introduction about the general properties of 331 models, and I will go beyond. And the motivation to go beyond is to understand lepton number in this class of models. And I will describe also two versions of extensions of this 331 class of models. The first one I call 3311, and the second one is 3331. And then I will draw some conclusions. So, what are 331 models? They are extensions of the standard model based on this gauge symmetry. So the only difference is the presence of an SU3 weak isospin instead of an SU2 weak isospin. And this is a crucial yet small modification to the standard model. So it's one of the minimal extensions of the standard model. So the presence of this new SU3 symmetry adds a new diagonal generator, which is T8. It can be written for the fundamental representation in terms of the 8 Gell-Mann matrix, and it has these diagonal matrix elements. And this is actually a class of models. These models can have different hypercharge embedding in terms of this new diagonal generator and the generator of the U1 symmetry, the Abelian U1 extra symmetry. So this is an important parameter, beta, and we want to say more about it. So what are the guiding principles for model building in this class of models and in general in extensions of the standard model? Well, extra fermions should not be added without a reason. So they must be introduced only if the group demands them. And they must be introduced only in vector-like pairs on the standard model group in order to have a minimal model, a minimal setup. And the new gauge symmetries must not have anomalies. So all the gauge anomalies should cancel in every gauge extension of the standard model. And the easiest way to go beyond the standard model and into a 331 model is just to replace the doublets of the standard model in terms of triplets, and that demands the existence of fields in these third components. And one must, if it is necessary to cancel anomalies, to introduce the vector-like partner of all these third components. Okay? So the setup is very simple, but there is a crucial difference between this class of models and the standard model. And it is this symmetry, this difference comes from the fact that the SU2 symmetry of the standard model is pseudo-real, while the SU3 symmetry in this class of model is complex. So one must distinguish between the triplets and the anti-triplets, something we don't need to do in the standard model. All the fields with two components are doublets. And that crucial difference is very relevant when it comes to cancel the gauge anomalies. So the third family of the left-handed quarks, this one, must transform as a triplet, or more generally in the same way the lepton triplet does, while the two other families of the left-handed quarks must transform as anti-triplets. And that is required by anomaly cancellation of SU3, because all the number of triplets must coincide with the number of anti-triplets in this case. And based on this class of models, which are minimal extensions of the standard model with fields transforming in the lowest dimensional representations of the new SU3, we have several times that this class of models have been discovered. The first class of 331 models discovered was by Singer, Valle, and Schechter in 1980 with neutral fermions in the third component of the lepton triplet. And the second time this class of models was discovered was with Pisano-Plates and independently by Frampton in 1992, where the third component of the lepton triplet has charge +1. But these are only two possible choices for the beta parameter needed to embed hypercharge of the standard model in terms of this enlarged symmetry. The common features of these minimal extensions of the standard model in terms of 331 gauge symmetry cancel only if the number of triplets equals the number of anti-triplets, and this is only possible with 3 generations. So it is often quoted that the 331 models predict the number of generations of fermions. The third quark family must be in a different representation with respect to the other two, and that leads to a very distinctive phenomenology in terms of flavor changing neutral currents at free level. And another common feature of this class of model is the presence of standard model vector-like fields, in particular quarks and one lepton, at least. So what are the possible values for the beta parameter in general? These values are restricted by the same embedding of the hypercharge of the standard model in terms of the new symmetries. That requires that this equation must hold, and if you require that the gauge coupling constant of the abelian part of the gauge group is real, then the value of the beta parameter is restricted to be less than 1.8, its absolute value, and requiring that no fractionally charged leptons appear in the spectrum implies that only 4 different values for the beta parameter are allowed. Yes?
They are heavy enough, in principle you could have fractionally charged leptons.
Yes, yes. But I think the restrictions are very, very strict, right? It must be very, very, very heavy. Yes. But we're thinking about some particles reachable by the LHC, for example, TV or something.
Isn't the issue more that they just cannot decay if they're fractionally?
Yes, there must be a symmetry that prevents them.
But even if you have the universe, they will stop annihilating and will be just around, and this makes the model that's why you don't have it. I thought this was the reason.
It's a C-logic constraint. There's a C-logic constraint in the whole
Yeah. Okay. So this relation can be relaxed for fractionally charged leptons, but if we restrict the models without fractional charge, in general, there are only four different values for this parameter. In fact, there are more than 4 models based on this symmetry, because switching triplets with anti-triplets and changing beta to minus beta is also allowed, and this leads to pairs of models with very similar phenomenology, suppressed by this scale, the scale, electroweak scale divided by the 331 breaking scale to the second power. There are other 331 constructions. These are 2 examples, and both of them are constructed not as minimal extensions of the standard model, but as unifiable gauge symmetries. These models are not based on only triplets and singlets. These contain fermions in higher representations of the SU3L. But in this talk, we will focus on the Singer-Weidel-Schechter class of models, which contain neutral leptons as third components of the lepton triplets. And there are only 2 beta parameters that allow this. Beta equal to -1 over square root of 3 with lepton triplets, and the opposite sign of the beta parameter with lepton anti-triplets. In its simplest form, the third component of the lepton triplet is just, it can be identified with the right-handed neutrino, actually the charged conjugate of the right-handed neutrino, or any other neutral fermion. This is the minimal setup of the SVS model. Sorry for the... Okay, so we have the lepton triplet, the quark triplets and anti-triplets, only right-handed charged leptons, and the corresponding right-handed up and down type quarks. And it requires at least 3 Higgs triplets in order to get the correct masses for all the fermions and the gauge bosons. In this setup, the web alignment is this. There is one web for one component of each of the Higgs triplets, and the symmetry breaking pattern is this. It is assumed that the 331 scale is larger than the electronic scale, and then we have two-step symmetry breaking. First we break SU3 into SU2, and then SU2 is broken down to color and electromagnetism. Yes? Two? Yes. Yes. So this is a particular web alignment in which not all of the neutral scalars acquire that.
So then you are breaking Lepton number with the
Okay. Right. What I want to discuss is what is Lepton number in this class of models. So that's the reason I put here the question mark. Yeah. So in this original incarnation, yes, that's the point. This Lepton number can be anything you want, basically. And why? Because, sorry. Well, let me explain first all the particle content. In this class of models, we have more gauge bosons than in the standard model. We have another set of charged gauge bosons. We have these two fields, W6 and W7, which do not mix if there is no CP violation, and the remaining fields, W3, W8, and X, mix into the photon, the Z and the Z prime. In particular, this model is from the 80s, is not viable anymore, as it cannot accommodate the correct oscillation data, the current oscillation data. It predicts Dirac neutrinos, one massless and two degenerate. However, there is a whole class of models within this SBS construction that can take into account different neutrino mass generation schemes. For example, one can build radiative neutrino masses or Dirac neutrinos with seesaw, or one can put discrete symmetries and describe flavor in terms of these discrete symmetries. For example, in S3, discussed in this paper, and an A4 model. But despite the versatility of these models, they all contain another peculiar feature, which is that Lepton number, oppositely to what happens in the standard model, Lepton number in the standard model is an accidental global symmetry. But in this case, Lepton number is mixed with, is a mixture of the new generator of SU3 and an additional global symmetry. And that's a very strange feature. A symmetry that is a combination of a spontaneously broken local symmetry and an accidental global one. And the question is, if this relation is consistent, can a symmetry be a combination of a local one and a global one? And for me the answer is no, because these two symmetries, L and curly L, do not need to be anomaly free, for example. So the anomalies of these two symmetries must cancel. And on the other hand, the SU3 symmetry is broken, this generator is broken, and we want to have models not only with broken lepton number, but also have the possibility to preserve lepton number. So there is a solution to this problem, and the simplest solution is just to gauge this curly L symmetry. And in that case, we will have a consistent model with gauged lepton number. And that can be done in several ways. All of them are extensions of this 331 class of models, and I will discuss two of them. The 3311 model, in which we just add another abelian symmetry, the curly L of the past slide. Or we can go even beyond, for example, in this 331 class of models, based on the gauge symmetry SU3 of color, SU3 left, SU3 right, and an additional abelian symmetry. And this class of models look ugly, sincerely ugly, but they have very pleasant features. I will try to convince you of that. So this class of model is actually more restricted than the 331 model. And that comes from the fact that one must cancel the anomalies of this extra U1 symmetry. And that's very restrictive and very pretty. And this class of models can display at higher energies restoration of parity. They are just left-right symmetric models, but with enlarged left and right symmetries. So let me introduce you the 331 class of models. These models are based on this symmetry. So we have the 331 model enlarged by an additional abelian symmetry. And in this configuration, one can embed B minus L, not only lepton number, but B minus L, into the generators of this enlarged symmetry. And we can have a fully gauged B minus L model. The anomaly cancellation of U1N leads to actually more restrictive models than the ones we can construct with lepton number in 331 models with an arbitrary curly L U1 symmetry, global U1 symmetry. So let me introduce you a realistic example of how this works. These are the quantum numbers of the abelian symmetries of the 3311 model. A very simple extension. It only has this additional field, this one, and this one with respect to the minimal SVS model I presented before. The role of this scalar singlet is to break spontaneously B minus L by Q units. And after the symmetry, spontaneous symmetry breaking, a remanent discrete symmetry is preserved if B minus L is broken by these two units. And that coincides with R parity in supersymmetry. And that's very surprising because this model is not supersymmetric at all.
But
So,
it is
yes.
very known that, this is meta parity. People have called meta parity or family
Yes.
deflection symmetry. It's all the same. It's always you break B minus L by 2 units.
yes,
And
yes, yes.
R parity
It's very
is despite its name not an R symmetry.
Mhm.
So it's a misnomer.
Okay, okay.
So that's actually
So
fully
in the papers we call it wrong parity. But it has the same structure as R parity. So
Yes, there are tons of papers and they're called family
course.
deflection symmetry, meta parity, or whatever. But it's always the same thing.
it's the same thing. Yes, I agree. So the point is that this R parity, this parity is is very useful because we have lots of extra fields in this 3311 configuration, and this symmetry can be used to stabilize, for example, the neutral fields in order to use them as dark matter candidates, for example. So in this particular case, standard model particles have parity equal to 1, and the lightest neutral non-symmetric standard model particle with the opposite parity is a natural WIMP dark matter candidate. In this case, the optimal candidate is the direct pair form from these neutral fermions. In this configuration, we have an additional gauge boson, which is N mu, and this mix with the other neutral gauge bosons in order to produce the photon as Z, the Z prime, and a Z double prime.
Is this guy coming in triplet with the leptons? This N1?
This N1, yes. So this neutrino right is the partner, the vector-like partner of this field, and the capital N is the vector-like partner of this one.
In the triplet?
In the triplet, yes. Vector-like with respect to the standard model. Let me introduce a more baroque example. This example displays Dirac radiative neutrino masses. So the configuration is almost the same as the original SVS, but the assignments for the new abelian symmetry are different. In this case, we introduce this complete gauge symmetry singlets. They are fermions, and they have B minus L equal to 0. And we have an additional triplet in the Higgs sector, which does not develop BEV. It's an inner triplet in this sense. And we break, for example, in this case, B minus L by 3 units through this scalar field, the scalar singlet, which is responsible for B minus L breakdown. So the charge in this class of mode, in this particular mode, is given by this combination of the generators of the gauge group, and B minus L by this one. So we have new fields with respect to the minimal 331 model. It's not a very large addition of fields. We have we implemented a discrete SZ3 symmetry in order to only avoid 3-level Dirac masses for this.
But do you need it, or is given by the B minus L?
No.
Because you are breaking B minus L like that.
Yes. But this is not the same. Okay? This is an artificial one, yes, an auxiliary one. This is only to forbid this term, this Dirac mass term at 3 level. We want to generate Dirac masses at 1 loop.
And the Majorana is forbidden by the...
Is forbidden by B minus L, basically. Yes, because it is broken in 3 units only. We introduce a soft breaking term for the Z3, which is a quatic term in the potential, modulated by this constant. The Yukawa interactions are this, and the scalar potential, the more general one with these quantum numbers for the fields, is this one. This is the soft breaking Z3 term. And so with this BEV alignment, these are the fermion mass matrices. We can see that the heavy quarks decouple from the light ones. The light ones are of electroweak scale, and the heavier ones come with the scale of S331 breaking. In this case, the B minus L equal to -1 scalars in the fourth triplet, in the inner triplet mix through this relation. And there is a small mass splitting between the eigenstates, the mass eigenstates that constitute these two fields. And the mixing parameter is actually dominated by this Z3 soft breaking parameter. Okay? So this term modulates how much these two fields mix. And that's important because we can now close this loop with the real and imaginary parts of these mass eigenstates of the neutral fields in the inner triplet. And we can form this scotogenic-like loop. But in this case, the fields that connect are the left-handed neutrino and the right-handed one. The mixing between the left and the left is 0, and so is the mixing between the right and the right. And the masses of the Dirac neutrinos are depend on the mixing angle of these scalar fields and the mass difference between them. It is very similar to the scotogenic model, but in this case we have Dirac neutrinos, and in this case, unfortunately, the Z3 discrete symmetry that arises from the breaking of B minus L by 3 units is trivial. In this case is 1 for the leptons, omega for the quarks, and that's all. Okay. So if one wants to implement dark matter in this kind of model, like in the scotogenic one must impose an additional.
Not the other way around. Otherwise, you will generate that.
Yes, it's the other way around. Sorry. So it's omega for the leptons and 1 for the quarks. Yes. Okay, and let me introduce you now the 331 class of models. These are left-right extensions of the standard model, but based on SU3 symmetries instead of SU2. The charge, the electric charge, is very similar to that one of the left-right symmetric models, and so is the B minus L gauge symmetry. In this case, due to the enlarged symmetry, only models with beta equal to plus minus 1 over square root of 3 are viable, assuming parity restoration at higher energies. So in this case, there are only 2 models, 4 if we consider the beta and minus beta pairs formed by switching between triplets and anti-triplets in the Fermi, in the lepton sector in particular. So this is an example of this class of models. The representations are symmetric on the exchange of left and right. The scalar sector we used is this. We use a bitriplet and 2 triplets to break the gauge symmetry. We also use sextets in order to generate Majorana masses, as is done in the regular left-right symmetric extension of the standard model. This is the wave alignment we used. So these 2 waves are at electroweak scale. This one breaks the 331 part of the model, and this one breaks B minus L. Yes. So this is the one possibility for the spontaneous symmetry breaking pattern. In this case, we break first the 331 part of the gauge group, and then we break the left-right part, B minus L basically. And we arrive at the standard model, and then at the electroweak scale we break it to color and electromagnetism. And there are several paths of symmetry breaking. For example, in this hierarchy, we can break firstly B minus L, and we will have an intermediate theory, which is basically a 3-3-1 with an additional SU2R part, and the remaining discrete symmetry. In this case, we also break B minus L by 2 units, and we have this parity. And in this case, we have several fields that can be identified as candidates for dark matter. We have also a direct pair of neutral fermions, several scalars, and even the gauge bosons. In this case, these are the W6 and W7. So, no, W6 for left and right. And that's all. So, I wanted to present you the basic features of the 3-3-1 class of models. These models predict 3 families by anomaly cancellation of the new SU3 gauge group. These models can be improved by gauging B minus L, and that improvement is actually leads to actually a more restrictive set of models and more predictive ones. There is much less arbitrariness in the construction of these extensions, even though they are based on larger symmetries. And so there are 2 classes of models I presented. The 3-3-1-1 class, which is the direct B minus L extension of the 3-3-1 class of models, and the 3-3-3-1, which is also an extension of the left-right symmetric extension of the standard model. And beyond 3-3-1 models also serve as a theoretical playground for the implementation of this matter parity without invoking supersymmetry, for example. Okay, that's all. Thank you for your attention.
Questions?
Can you briefly summarize the phenomenological constraints on these 3-3-1-1 and 3-3-3-1 models?
Well, there is a lot of models that you can construct in this class. So you can have, for example, in terms of leptons, you can have models with Dirac or Majorana neutrinos. You can have all the variants of seesaw in Majorana neutrinos, radiative ones, etc. So it is very hard to mention, to summarize the phenomenology, because it is a whole class of models. It's very, very diverse. So the ingredients you will always have is extra quarks, for example, in different representations. So you will always have flavor changing network currents at 3 levels. You predict the existence of vector-like quarks also, and only 3 generations.
So generally, limits on flavor changing neutral currents.
Yes.
No,
Yes.
no electroweak precision observable.
No.
The spectrum on the extra gauge ball.
No.
Generally, this is the.
Yes.
More questions?
So here your neutrino mass generation is
Yes.
radiated at one loop.
At one loop, yes.
Do you need to invoke certain small coupling constant because one loop factor is just 1 over 16 pi squared?
Yes, yes, yes. So, but the point is that you have more constants. You have, for example, this constant that. So you can play with the scales, of course, the symmetry breaking scales, but you have also a quartic coefficient and, sorry, 3 quark coefficients, and you don't need to invoke a very large mass. For example, let me put, no, I'm going the other way around. You can have Yukawas of the order of the electron Yukawa with TeV scale masses for the singlet fermions, and you can also invoke almost degeneracy between the two scalars involved in the loop. So you can play with a lot of scales in order to have realistic mass. Yes.
More questions?
Yes.
Yeah, I have a question. I mean, there are a lot of three, but without one models around it, known as trinification.
Yes.
Is this
For example, trinification is only 3.
I know, but
Yes.
are your models somehow related to those? Or
No. This is something like a flipped trinification.
Okay.
The last one. Okay. So it's trinification plus another U1. Yes. And you can change the quantum number assignments. But this is not based on trinification.
You can also get generations predicted trinification.
Yes. So this is the Fonseca model, actually. The flipped one. Yes. This one.
So how is the unification scale in this case? It's much
In this
lower.
case, the point is that this class of models do not unify well. They don't fit in SU5 nor in SO10. Yes. You can check how the coupling constants run, but they don't fit in a gap. Yes.
So you extend the gauge sector?
Yes.
More questions? So this, you are not mixing the vector light with the quarks, but in principle you can do it
Yes, of course.
and have some violation.
Of course, yes.
More questions? If not, let's thank Carlos again.
Big mind.
En capa.
And vaca. Exacto. Pero está chapas, entonces hay que hacerlo bien.
Si tú puedes hacerlo.
Bueno, mañana.
Se puede hacer dos formas, no necesitas una Z3, puedes solicitar una Z2. No tampoco. Sí, entonces el término que no puede ser Z2 sería I1 y 2. Eso sería la que lleva. Esa no está organizada, nada más marca el término. Entonces así se rompe con todo. Y entonces se puede romper ese
A ver si llego, porque yo he llegado a las 3 menos 10. Ya para llegar a las 3 y media, pues entonces igual llego muy pronto. tengo una pregunta.
O el Uber o lo que sea.
No, no lo son.
¿Hay fotos?
Igual mañana antes de la comida o durante el break.
Yo vengo el jueves y el viernes mañana. Tengo que conferencias en la mañana y llegaría hace ya algo.
Photoshop.
Pues toda esa clase de modelos.
Podrías así como que
Sí, pero no. Ya lo checó.
Bueno, el pico de audiencia después de
Yo ahí no sé nada de esto, pero ahí
sí, no vale ver. Porque ahorita también, ahorita ya parece que sí, eso,
y entonces la manera Ocean se parecía a lo que
sí, parece
Sí, yo recuerdo el paper de Sofía que básicamente podías tocar con el breaking de
incluso mejor que justo.
pues no era claro si se podía directamente o
¿Cuál fue el primer?
La segunda
la segunda es Helen
Y me dio esa impresión, o sea,
o sea, lo podía mover a
bienvenida.
pero eso es una
Va a ir a ciudad de enfrente, no sé, ¿sabes? Va a ir a contratar una comida mexicana o
el término
hay un hotel, entonces.
Pero
ahí se lo lleva al hotel y ya, ok.
sí, es global.
Ok, justamente unos minutos ya vamos para
Tomar algo ligero.
Entonces, impresiones que no está bien definido.
Ok.
Y luego,
bueno, porque si te ayudas es una buena motivación.
Sí. Sí, el problema es que tiene que hacer una solicitud para los bocadillos. Más bien lo que entiendo es que la pregunta es a qué va. Podría ser.
Es que entonces es una motivación.
Pero le puedo decir simplemente exactamente, si ella llega al 20 y les falta como el vemos hacer, o sea, nos presta la sala de 1 a 3.
Normalmente veo menos esta, pero me va a poner.
Es que tienes que ver con las dos que todo el mundo va a estar comiendo.
pues está bonito.
José is actually staying at the hotel. Yes, so I'll take you to the hotel and then we'll go from there.
¿Tú te quedas?
Solo 24.
No, pues yo veo eso combinado y
Claro,
Está yendo como 18.
pero tú llevas más, ¿no?
18 a 20.
O yo no he preparado nada.
Que ya están como perdidos, pero simplemente los veo una parte de 20. Pero van entre 18 y 20. Sobre todo porque el miércoles de la siguiente semana voy a hacer un lío porque también claro. O sea, todo es un lío. Entonces estaba pensando sobre todo en esta bienvenida que queremos hacer. Please take the photos and
Pero pienso que además este modelo
bueno, él
es más
todo el día, pero yo creo que son las sombras.
¿Son de acuerdo?
¿Quién sabe qué pasó? Hace un mini taller.
Creo que este modelo más podríamos número de tonos, dos unidades.
So we'll meet the outside for the picture. No.
Este sigma.
She made the announcement. Who made the announcement?
Sí, algún lazo, claro que sí.
Or somebody
Eso es
Oh, you got cancel, whatever.
No, la idea es que...
sí, ahí se canceló. Pero para generar más pequeños,
Porque estaba
incluso rompiendo lo que es igual a 2, pero nada.
¿Habrá
A un
gente ahí
lazo.
abajo esperándonos en la fuente?
Claro, la
¿Quién lo dijo?
Si están ahí, nos tomamos
Lo dijo igual.
Bueno, yo voy a ver la una y ya veo todos los detalles. No sé, ahorita les pregunto.
José va a regresar a hotel y va a comer, lo voy a llevar. Él y Paul.
Y esto, por ejemplo, también no es necesario, pero
vas a cenar, lo voy a llevar.
Sí, la
puedes
reservar.
reservar
Más que vas a cenar.
más
Y simplemente la prima se queda.
Échale nada
Gracias.
más.
Gracias.
también.
Está cotorro.
¿Está cotorro?
Lo voy a hacer una foto para ver si el próximo semestre que vaya a cotorro.
Bueno, pues sí, muchas gracias. Vamos a hacerlo de una, dos y algo. Para que por cierto, ustedes. Bueno, tú, por ejemplo, ¿no quisieras estar con Kelvin?
Depende de... Sí, quisiera, pero el problema es que el lunes y martes están los del proyecto Reino Unido. Entonces,
puedes abandonar.
les puedo decir, y a lo mejor ellos vienen también, porque viene mi colega del Reino Unido, por todo, tienen tres.
No van a dar plática, la idea es simplemente to welcome Helen Green and say hi and eat something here together with all fellows, students and everybody.
Okay. Sí, haré lo posible por...
¿Todavía? ¿Ya la apuntado?
Yo aquí lo tengo.
So you're going to for dinner, right?
Now with Professor Vance, next set of lectures.
Okay, hello again. Again, please interrupt me at any point if there are any questions. So, I'm just going to repeat the very last part of the previous lecture that we were talking about orbifold, because this is a confusion. So, an orbifold is not a manifold. The starting point for constructing an orbifold is often a manifold. So in this case, it's just a torus. It means you identify this line is this line, and then you run out here, out here. But then you do something which turns the thing to something which is no longer a manifold, which is you mod out some symmetry of this thing here in this case. I decide to mod out a rotation by 180 degrees. That means this point gets identified as this point, but then this point identified as this point, and there are four special points which are fixed under these operations. So this point obviously is invariant under a 180 degrees rotation, but this point is also, because it will get mapped to here, but under the torus identification this is the original. So it applies to these points as well. And what you can do now, you can convince yourself that if you run out, for instance, here, you come back here. If you run out here, you come back here. So you can fold these things together. I've shown this animation. So you can identify these edges together. And this gives you a picture of the orbifold, which looks like a ravioli or a pillow. That's what people call it in the old days. So there are these special points, these are the fixed points. And these are the points which are somehow not regular points of a manifold. So here in a certain way have infinite amount of curvature. These are sort of singular points in polyparticle geometry. And yeah, these are the fixed points. Otherwise, this is just a smooth manifold. and it looks like they have really working. Now, of course, if you do these things in the context of a gauge theory, there are very interesting possibilities that arise, because you can now associate this to this 180 degree rotation, so the operation in the gauge group. And what this will do for you is it will break down the gauge group, which you started with, to smaller subgroups at these different points. And if you consider settings with background fields or Wilson lines, so these gauge groups will generally differ. So there will be different gauge groups at different points. And the low energy theory, that is, if you go now to distant to energies which are much smaller than the compactification scale, which is set by the radius of this object, the low energy theory will be just the intersection, the group theoretical intersection of these different things. And this is sort of very nice, because now you can entertain the possibility that one of these groups will be, let's say, SO10. What does it buy you if you have an SO10 here? Well, we already reviewed the group theory of SO10. We know that if you have an SO10, an electron lives here, or the upward will live here, because in some representation theory, SO10 will force you to buy a complete generation, a complete 16 bit. And this can explain why matter appears in complete representations. Whereas fields which live at other points or in the bulk here, which can propagate everywhere, they can naturally appear as split multiples. And this is how doublet, triplet splitting in the orbifold construction works. So you can have easily explained the coexistence of complete multiplets, sitting somewhere here, and split multiplets. Now, of course, this is all some geometric picture. You can really do string theory on this background. You just add strings to the scheme. And what is important is that there are two different types of strings. There are some strings which are just closed strings, which can travel everywhere. And they are just closed in the orbifold space and the Toro space. They are always closed for these three things. But then there are additional strings which are only closed because you identify points which are related by the 180 degree rotation. And these are the so-called twisted strings. And the geometric interpretation of these strings is that they sit at these different fixed points. And this is precisely how you can now explain generations. So you will have cyclic generations with the twisted strings, and they will be attached to one of these fixed points. So of course in the field theory description we would refer to these green things as bulk fields. These are fields which can allow to travel everywhere. And the red things to braid fields. These are fields which are really attached to these fixed points. What is however important is that in the context of string theory there is actually no singularity at all. So from naive point particle geometry you would have singularities here and there. But since strings are extended objects, its stringy description is completely regular. There is no singularity in that. You can really just work very simply there and can do a very, very simple quantum mechanical computation to find out what the strings really are. Because in string theory it turns out that you cannot say, oh, I put this red string here. Rather you have to compute what these strings are. You just compute the excitations. And then you ask, what are the masses excitations at these different levels? You can do that in string theory. This is just a basic quantum mechanical computation which you can do after the first lecture of quantum mechanics, or course in quantum mechanics. In principle, you can also do that in field theory by putting in here some freaky manifolds like the Tucci-Hansen spaces or whatever, and then you can use powerful index theorems to get the same result. The same in the end, but in the string context is much simpler. And as I said, if you have such a setting, you can explain complete generations, because each thing sitting at some fixed point will have to come in a complete multiplet of this symmetry, like 16 letter of SO10. So that leads to a geometric picture where you have 4D spacetime, But now, of course, we have extra dimensions. We have some tricky internal space. And what might be true is that in this internal space, there are certain regions or corners where you have 16 plates of a localized SO10 gauge symmetry. The effective symmetry or gauge symmetry of the full thing is smaller than it, it will be the intersection of SO10 and various other groups. But here at this point you have already features of a standard 4D duct. You have a 4-dimensional point with a 16-plate segment here. And if you have several of these, then you have several 16 plates. So then we have to, of course, use this and let's try to find some string models, just using this in a certain way as a guiding principle for the construction. And was sort of successful or rather successful. So there are many models, so coming back to your question yesterday, there were many models where you have the precise standard model gauge group and just the at least chiral matter content of the standard model. There are no exotics. So typically all these string models are full of exotics simply because you cannot just choose the representations, you really have to compute the massless excitations. You typically get things which you don't like, but here this doesn't happen. In addition, there's really just a standard model gauge group, plus maybe some hidden gauge group, which however doesn't talk to the parameters of the standard model, the standard gauge. So the end just boils down to the standard picture, of course, where you have these known gauge interactions and gravity. Because of these features, of course, you can entertain the possibility of standard supersymmetric gauge coupling unifications. The gauge coupling run and there's no completely state which locks up the running, so this gauge coupling is unified very precisely. In addition, there is this R symmetry which kills all the proton decay operators. The proton is sufficient. This is typically a problem in these models because you generically get operators which spoil, which simply make the model inconsistent. And there are many string models which are like ruled out by just looking at them because the proton is very short-lived, but this doesn't happen. And what is of course important for this talk is that the Caesar mechanism comes automatically. So you look for a model which has a standard model gauge group, the standard model matter field, and what you automatically get, and this is something which I'm going to explain in more detail in a second, is the Caesar mechanism. You don't have to work for it, it's just there. Of course the arguments are the same as from bottom up, but there's nothing what you are at the standard model that protects the right neutrino from acquiring a mass, but this explicitly happens. Another neat feature of these things is that you can start computing Yukawa couplings. Usually it's a quick puzzle, what are Yukawa couplings, where do they come from? In this setting, of course, you can start computing. And it turns out that all Yukawa couplings are suppressed. They only come after certain fields acquire a BEF. These fields you may refer to as flavors if you wish. But there's always one exception, and this is the top quarter. And this is something which automatically comes. We never understood really why. We could have been unlucky that the tau is always the massive guy or the bottom, but it's always the top quark. There are also not two of them, there's just one thing which is the top quark. And the at tree level, the gauge, the top Yukawa coupling is predicted to coincide with the gauge coupling at the high scale.
At this level, what distinguish the quark?
No, you just compute the Yukawa matrix. And in the Yukawa matrix you find that there's one entry of the order G. So you get a Yukawa coupling, you compute the matrix, and then you have all sorts of singlets here over some number to some power. This is true for all couplings except for one. And you can choose the basis in such a way that this is the 3 entry, and this is predicted to be of the order G. And this prediction is also not something which is, of course, this prediction is very easily understood because in this case, both the parts of the top multiplet and the Higgs come from extra components of the gauge fields. And there's only one weighting interaction with each other, which is the gauge coupling. But the important thing is that this doesn't happen for any other standard model particle. It's just there's one quark doublet, one uptype quark, and there's HU and also HD, which have the property that they come from this so-called untwisted sector.
So it doesn't happen for the bottom layer?
No. Generically not. I mean, you play, if you know search long enough, you may find models, but typically not. So Stuart is now bugging Saul to look for partisan models, but this will happen. So there are partisan models which you have to break and so on, and then you have also the bottom. But at the very, for the vast majority of the models, good. And also there is always some, okay, yes, the whole story is of course richer. The full categorical string has a gauge symmetry, which is E8 plus E8. And then there's of course always the second E8. And once we accommodate or get the standard model from the first E8, then the second E8 gets broken to something, which is actually fixed. So once we add the Wilson lines in such a way that we get the standard model, then we get the second E8. We just computed at which scale, so this is always some SUN troop or some other troop which gets strong at some intermediate scale. We computed like somehow the another one of lambda QCD for this kind of theories, and it turns out that there's a statistical preference in this ballpark. But this is rather nice because if you look at the models of dynamical supersymmetry breaking, this leads to a gravitational mass in the range of TeV. So this is something which would naturally give you something at TeV scale. And yeah, automatically, this is related to the fact that these guys come from the untwisted sector. There's a solution to the new problem. You usually have a problem, of course, of the standard sector in the MSM that you don't know what the new parameter is. Small, I told you that I was looking for a symmetry which somehow forbids the new term. And this symmetry is given by an R-symmetry. Of course, R-symmetries are always broken because once you break supersymmetry, the superpotential acquires are left. You get R-symmetry breaking, but the super term is then given by the Barfield expectation value of the superpotential in Planck units, which is the gravitational mass, so you get a really appropriate value term. Good. And what is really neat about all this, so Saul has this very nice code where we can look for models. And you get, of course, tons of models, most of which are wrong, but you can just start picking out models which you don't like and just keep those which you like. And then there's some fraction of models which has these features. So you just get the standard model gauge crew, the meta content, and so on. And the important thing is that once you somehow filter the models in such a way that you have these features, then everything else is sort of automatic. So you don't have to put this in, this comes automatically. In particular, the CISO mechanism in these models. So if you believe in these models, you would say CISO is true. Of course, maybe there are other models, but at least in this case, it's something which always happens. And this, of course, is kind of, raises the question, what is the CISO in this kind of construction? And to this end, we have first to clarify what is a right-handed neutrino. Well, a right-handed neutrino from the standard model perspective is just some state, some fermion, which has 0 quantum gauge quantum number, so it's a singlet under SU3 color, it's a singlet under SU2 doublet, and also has 0 hypercharge. But it has some lepton number 1. This is a right-handed neutrino. And you can now ask, how many are those? Because in these 3D models, of course, you cannot just say, oh, I introduced these by hand. It's just impossible. You have to get them as massless excitations of these compactifications. And what you find is if you just count these states, you get typically order 10 to 100 of these right-handed neutrinos. So you do not get 3, which you would naively expect. But once you identify to this P minus L generator and so on and so forth, you find that they're typically order 100 neutrinos. And this is of course something which goes in the right direction, as already mentioned by John. If you now compute the effective neutrino mass operator, by integrating out all these 100 right-hand neutrinos, it means you certainly sum all these diagrams, but neglect the kinetic or the derivative term for the right-hand neutrinos. This gives you the Weinberg operator, but what is important here is you have 100 contributions. So that means you get a larger result than with just big contributions.
This right-handed neutrino you are talking about is the heavy.
They are all heavy. They are all heavy.
There's the heavy one.
Yeah, but they are 100 heavy. There's always an odd number because of.
Not means of the scale of the.
Yeah, so we have all 100 contributions to the effective neutrino mass operator, and this means you have a small suppression of the scale, of the effective season scale, because if you multiply, you can do some random walk or whatever. But you get an order 10 to 100 suppression of the effective season scale, so that means this is somewhat more in agreement with a season scale of 10 to the 14. I'm not claiming that you get precisely 10 to the 14 GeV from that, but at least it goes in the right direction. So it's easier in this framework to accommodate the observed delta M squared atmospheric and solar, because what is sitting here is not the gut scale, but something like gut scale over 10 or other. So, and what happens is we have now looked at tons of models. Of course, always in this corner of the landscape, this is a chaotic corner, this might be one corner, we don't know, but it is in this corner. And CISO is a generic thing. You don't have to do anything for it, it's just there. And works out rather well. And I apologize now for that. I really don't know, there's some LaTeX bugs, so people of course have looked at this and have looked at statistics. They just added 100 neutrinos and put some random couplings. And what they find is statistically large mixing angles and mild hierarchies are preferred. But I'm sorry, Monjun had in my slides when we showed data, I was unable to fix it. There's some big LaTeX bug which I really don't understand. Anyway, so the bottom line is that you get there are arguments. Of course, you may not like all this playing with random numbers, and I would fully agree with that, but at least okay. If you like playing with random numbers, then there's a statistical preference for large mixing angles and mild hierarchies, which is of course something which you observe in Leptons. Another thing is that if you have more than 3 right-hand neutrinos, the constraints on leptogenesis get somewhat weakened. So you know usually there is a lower bound on the reheating temperature for successful leptogenesis. And this clashes with some other constraints very often, but here this bound on the right-handed neutrino mass gets somewhat relaxed. So you can live with right-hand neutrinos of the order 10 to 8 GeV without evoking any resonances or some long-term leptogenesis. So it's just because the number of right-hand neutrinos is larger. You can circumvent the so-called casus Ibarra bound, which maybe should be called Moriyama, Hamaguchi, Yanagida bounds because they happened first. But anyway, so these things go a little bit over. Good. So, and you can now, of course, discuss all these sorts of implications. I also don't know, I mean, I personally don't like playing with random numbers, but I'm also unable to compute these couplings of the neutrinos with a high precision, so I cannot make more statements, and it seems to go in the right direction. And now I want to sort of switch topic a little bit, because we have already started this, and we are big experts on all this CP and so on. But this is something which we got excited about in the recent years. What John already mentioned a little bit. This is the question of CP validation. You see, if these string models are to really give us a description of nature, they should also tell us a little bit about CP validation. Should tell us why in the fermion sector of the standard model, at least in the quark sector, we know that there's CP validation, and maybe also tell us what the solution of the strong CP problem is. So, because of course flavor, CP violation has only been observed in the flavor center, it's very natural to seek some connection between flavor physics and CP. And what I'm going to discuss here is the relation between flavor symmetries and CP violation. Of course, there's the standard puzzle, which you all know probably, that there's the strong CP problem, which tells you that which is the question value coefficient of the G-dual term of QCD is so small, and the solution is typically the axiom. One of the most promising solutions is the so-called axiom, that you make this coupling a dynamical field, you promote this for a field, which is the axiom field, which comes with the high dimensional coupling, there's the axiom K constant. And one amazing thing is that if you minimize the potential for the field after you take into account the non-temperature dynamics of QCD, you find that the minimum for the axiom is at a point where the effective theta QCD angle vanishes. And this is of course something which sometimes doesn't get appreciated enough, because I mean, just making the axiom that the dynamical field is not enough. I mean, there is always the quotation mark the miracle that the minimum occurs at a point where this kind of CP violation is switched on. Of course, if you look a little bit more closely, then you will remember that there is the so-called Waffer-Witten theorem, which tells you that the stationary points in the potential, that the CP violation is preserved, and this is essentially what happens. You are guaranteed to find this minimum, and this is the one of the most promising solutions to this strong CP. So, and I'm going now to sort of try to go in a slightly different direction, mainly to motivate a different understanding of the origin of CP violation. And to this end, I want to start very, very basic, QFT, and just to review what CP really is, because there's sometimes a confusion in the literature. So, of course, in standard QFT, you have typical scalar field operators. Scalars, you have representing confirmers, and you have, of course, the standard annihilation and creation operators. And what CP does essentially is exchanging the particles and antiparticles. So there's a mapping from this A to B and from B to A. This is a CP transformation. In case there's a basis dependence which can be sorted as phase vectors, but this leads to some CP transformation at the level of the classical field, so you just map the field to the conjugates. Of course, evaluated at the points where the Minkowski coordinates get reflected as a parity transformation. So now, and this is the main observation which I want to make here, there is sometimes some confusion, some confusing statements on the relation to the groups of the system. If you look at the continuous groups, which we use for our gauge groups like SUN or EA or whatever, then there is a relation between this complex conjugation or the CP transformation and the automorphisms of the group. Specifically, if you look at SUN, that you know that there's a symmetry of the Dynkin diagram. Generally, in all the Lie groups, the outer automorphisms are controlled by the symmetries of the Dynkin diagrams. For the A N series, for the SUN groups, there's just one symmetry, the C3 symmetry, which just flips these nodes. And this is, of course, the standard complex conjugation. So this is nothing but the statement that all SUN for n larger or equal than 3 have complex representations, and you have a complex conjugation. And now it so happens that this complex conjugation does the same as the complex conjugation of CP, and therefore some people confuse this outer automorphism with a CP transformation, simply because this happens to these things happen to coincide for the standard model gauge group SU3. So that means if you have the standard model, which has this nice series in Dinkel there in terms of embedding into SU5, SO10, and A6, CP always involves the outer automorphism of the nodes. So there seems to be some relation. And this has been then, people have then respected, okay, then we do the same for discrete flavor symmetries and say, okay, the outer automorphisms are our CP transformations. But the point of Neutrinos in my talk is that this is absolutely not true. So this is just a coincidence in a certain way that this happens with these SUM groups. It does not happen for general groups. It's actually something which is already not true for continuous group, the continuous group S08, where the automorphism group is in S3. So the Dinkel diagram has this form of a Mercedes star, and you have a larger automorphism group, and there this statement, the naive expectation, is already not so good. So let's now talk about settings with some discrete symmetries, some flavor symmetries, and generalize the notion of a CP transformation by allowing here some, instead of the phase vector, we now allow for a unitary matrix. The reason being that these A and B fields can now come as multiplets of some flavor symmetry. Good. So we can do that, then we can do some standard tricks from the literature and look at constructions of, let's say, T prime or A4 models. And look what a standard CP transformation does. And if you look here at this, these couplings, you see that there are certain complex coefficients. If you would now replace all of these fields by their complex conjugates, you will map something which originally was invariant under the flavor symmetry to something which is no longer flavor symmetry. Because these coefficients here, these Clebsch-Gordon coefficients, are not the Clebsch-Gordon coefficients for the conjugate fields. You can rectify this by introducing a so-called generalized CP transformation. They do not just subject these fields of the triplet of such a field to complex conjugation, but you also exchange two of those. If you do that, then you map an invariant coupling to an invariant. And this was basically the argument of these gentlemen to say that this is, of course, the way how the CP is to be implemented at the level of these discrete groups. Good. So this is the general CP transformation. And there were certain recipes. I'm not really going to discuss this. I just want to make the point that this is ultimately not the full truth. It turns out that there are simple criteria that tell us what is a CP transformation at the level of the discrete groups, which really has the physical properties of a CP transformation. Namely, that it really maps particles to antiparticles. I think really important point is that you cannot take any arbitrary automorphism, but the requirement is that this be a physical CP transformation says that this U has to be something which is called class invert. That this outer automorphism maps all group elements to their inverse. And just to translate these statements to statements made in the literature. So there are, of course, proper CP transformations. And if this CP transformation is a symmetry of your theory, then you are guaranteed that all these so-called CP violating observables vanish. For instance, decay asymmetries, CP violating decay asymmetries will vanish if this CP transformation, this kind of CP is a symmetry of the diffusion. And of course, in this case, you can really relate this CP transformation in the usual way to baryogenesis. You know that all of these Sakharov conditions is the requirement that CP be violated. But what Zakharov really meant in this context is a physical CP transformation and not some so-called Chener method. There are so-called CP-like transformations, which are outer automorphisms of the group, but that's all they are. They are just not really any physical CP transformations. In particular, if you demand that these be symmetries of your Lagrangian, we're not guaranteed that these amplitudes will vanish. In particular, breaking these has nothing to do with this Zakharov conditions. So, unfortunately, in the literature, in some parts of the literature, these things have been dubbed generalized CP transformation. But I think this is not really good name for those because they are not really related to what we usually think of CP, like in the sense of Zakharov conditions of scalar symmetries and so on. So these have no connections to the observed CP violation. Good. Then there are certain recipes which tell you if you can find or what properties or how to find such CP transformations. And I'm not really going to discuss this in detail. There are some technical details which you can use here. But the most important point is that there are certain discrete symmetries which simply do not allow for a physical CP transformation. And this is something which is completely different from all our experiences with groups. For all continuous groups, you can always impose CP. So you have a gauge theory or symmetry with some global group symmetry, you always can impose CP. This is not true at the level of the non-abelian finite groups. There's a certain subset of finite groups for which you can never impose CP. So you have the symmetry and then CP violation is sort of automatic, and this has been pointed out by June 2009, long time ago. There are of course a lot of groups where you can impose CP. The simplest ones are those in which you then even can find a CP basis, and in the CP basis all the Clebsch-Corbin coefficients are real, and the CP transformation is really just the usual thing. Field goes to its complement. There's nothing mathematical. There are somewhat more subtle groups where you have no basis of this type, but still CP can be preserved. So there are some complex couplings, but these complex couplings do not enter CP transformation. And it turns out that the groups of which have the property that they violate CP, they are not very rare. In fact, all non-abelian groups which have an odd number of group elements are of this class. Whenever you have a non-abelian finite group which has the property that the number of group elements is odd, you already know that you cannot impose CP. So in particular, this delta 27 and T7 is of this kind. And then there are of course others like this delta 54 which will play a role in this subsequent string discussion. And then, of course, there are many models where you can impose CP, like this prominent A4 is an example, G prime is an example, S4 is an example. There are tons of models based on these groups, and for those you can, of course, impose CP, but for this one, which is also these two have to employ the model, you actually cannot. And then there are these more exotic groups are a bit rare. Now, of course, the question is if I now advertise in string theory, then of course I want to perhaps only use these observations in string model building. And it turns out that one of these CP violation, like in groups, automatically pops out in the very simplest orbifolds which have been, the first which have been discussed, as something which can connect particle physics to string theory. And this is the C3 orbifold. So this has a very long history. In 1987, people started like this is the 3 orbifold. Here the pillow, which I drew before, has a slightly different shape. It has only 3 fixed points, and it has certain fixed points, certain states sitting at the fixed points. But now you see that if you have no background fields, all these fixed points are equivalent. So you can in a certain way rotate this thing by 120 degrees, and it looks the same. You can somehow map these, and then there are other transformations which you can derive from the string theory. So I'm not going to detail, but if you look at all possible symmetry transformations of the effective theory you get from this plane, you end up with a delta 54 flavor symmetry. So this happens here in the geometric way, very similar to what Francesco mentioned in his talk, except that here we will took all the symmetries into account which really occur here, and the symmetries which we get here is not just the symmetry of the solid, it's always larger. Good. And the most promising model, actually, which has the symmetry, is something which Saul did in the recent years. So this is some model from UNAM, and this has precisely the feature. You have here the multiplicity of quarks and leptons, which really is related to the three equivalent fixed points here. So each of these fixed points carries one generation. Now you have to see three permutation symmetry, other symmetries, and you get a delta 54 symmetry with these guys. What is somewhat subtle here is that the right and neutrino candidates identified in the analysis transform as a 3-bar. There are two different triplet representations, each of which comes also with a bar version. And okay, this is a 3-bar. Good. So these quarks and leptons transformed them as triples or anti-triples of this delta 54. And I already told you that this delta 54 is CP violating, therefore you would expect that CP is violating. This turns indeed out to be the case, but it's actually a little bit non-trivial to work this out. And the reason why this is not so simple is that the representation content of this model is rather special. Delta 54 has triplet representations. It has one-dimensional representation of doublets. But at the massless level of this model, there are no doublets. And if you look at the outer automorphisms of delta 54, the outer automorphism group is in S4, then you find automorphisms which are classed in blocking only for the triplets. And these work as physical CP transformation as long as there are no doublets in them. And at this level, at the level of the only massless modes, you would say that you have a CTP candidate. But it turns out that, of course, these are string models. We also now have something to say about the massive states. And there are massive states which transform as doublets. And here is a cartoon of how they look. These are strings which wrap around two different fixed points in the opposite direction. And the doublets of delta 54 are linear combinations of the blue, green, and red strings here with certain coefficients. And in addition, there is also this object, which is the fourth doublet of this group. So there are these doublets. And now you probably all, many of you know that in order to find or establish CP violation, you have to establish some CP violating observable or basis invariant, and you can always depict this in a certain way as a contraction or as a Feynman diagram. And here the Feynman diagram is something which involves the triplets, which are the solid lines, and the doublets, which are the dashed lines. And this is a CP violating observable, because if we compute the imaginary part of this is non-trivial, and of course this thingy is independent of basis transformation, because all the basis transformations are cancelled out. So this is a CP violating basis invariant, very much like the Yarlskog invariant, except that this is of course a bit more lengthy. I'm not saying that this is the dominant source of CP violation here. We can cut now this and make this a K amplitude for some doublets and so on, but it's just an existence proof that there is some explicit CP violation here. And I have not much more to say about this. There's no phenomenological implication, have not been worked out at all. But it turns out that here in this string models, you automatically have CP violation in the flavor symmetry. So you have automatically a relation between the flavor symmetry and CP. I'm not claiming that I can compute the delta phase of the quark sector. This is great to an absolute overstatement, but at least all the necessary ingredients come out for free. And I stress that, of course, we didn't invent the C3 omniform for that purpose, which has been around since 1987. What is new, of course, is the observation that these things automatically occur. Let me also briefly comment on neutrinos and other constructions. So there are other string models. There are string models where there is where you get exponentially suppressed Majorana mass forms. I should stress that all these models, they say you find these ingredients here. There's no explicit model. They have just a standard model with these neutrinos and nothing else. You always have something which spoils these models, but at least in principle, you can find models where this is restricted. There are also models where you can use this exponential suppression in order to explain Dirac, the smallness of Dirac recovered particles. There are string models in which you get exponentially suppressed Dirac recovered particles. And as I said, I mean, this is all, the ingredients are all there. There's, however, not yet any single model based on these constructions, which looks anywhat similar to this standard. There's also F-theory. In the F-theory, people have identified the writing neutrinos with certain Kaluza-Klein states and concluded that in principle there's also some C, so that this could be excluded. Again, I'm not aware of any explicit model which has looks like a standard model which has this in. But certainly there's huge hope that ultimately someone will find such a model. There are other models where you get to explain the smallness of the Dirac neutrino mass, as already mentioned in Chun's talk. You find it as a relation between the U parameter of the MSM over the Planck mass, or a ratio between the soft mass and the Planck mass. So what it means is, what we usually do is, of course, in the CISO, you say the neutrino mass, we write the neutrino mass is something like electroweak scale over Majorana scale times electroweak. This is the usual CISO relation, but now you can, of course, go and replace this ratio by other ratios, like this MC half over M prime, which goes back to Majorana and collaborators, and many. This is one thing which they find as possible to achieve this. Good. And if one is to entertain this possibility, which we already did this, you can of course ask what are the alternatives. There's a longish literature on these, and one thing which comes into your mind is to replace the neutrino mass, explain the suppression of the neutrino mass as the ratio of the gravitino mass of the Planck mass. And then you would relate the smallness of the neutrino mass to the smallness of asymmetry breaking. Because the gravitino mass is proportional to the vacuum expectation value of the superpotential, and the vacuum expectation value of the superpotential is the order parameter of asymmetry breaking. And you get effectively sub-operators, and this might, of course, explain small Dirac and recovered particles. The only issue is, of course, that if you want to play this game, you have to also explain why this operator was not there to begin with. So that means you have to make sure that this coupling is zero and gets only induced from this source. If it's there right from the beginning, and of course you do not have suppressed particles. So you really have to, if you really want to play this game, you have to forget the Weinberg operator and relate these neutrino mass to asymmetry breaking. And this is just to mention that if you do a bottom-up analysis and look at models with symmetries and consistency conditions, then you find a lot of possible charges which do the job. So So there's a lot of symmetries, and what Mouton already stressed, of course, that these symmetries do not just explain Dirac Neutrinos process, they also explain why the mu parameter in the MSSM is small, and explain why the proton is long-lived. It's not just that this is the purpose of these symmetries is that neutrinos are dynamic. But in a certain way, you can say that there are certain solutions to the mu problem and the proton decay problem of supersymmetric models, which automatically give you small Dirac neutrino classes. And you may get them from strings, but you cannot say more than you get these types of symmetries from these geometries. I have not ever looked at explicit realization. There are explicit examples, and okay, in the very last part of this talk, I would like to just set the stage from Mouton's lectures and just do some very basic discussion of cosmology. Mouton will then tell us much more about electrogenesis and so on and so forth. So they are very basic things. So this is again very basic. We know, of course, the universe is expanding because we find that distant galaxies get redshifted. And this is a cartoon of redshift, so which in a certain way relates the wavelength of an observer, which an observer sees, to the wavelength of the source. And the expansion coefficient here is nothing but the so-called Hubble rate, which is of course known very well today. So this is some parameter which is known to an amazing precision, and this tells us that we are living in an expanding universe and also children of expand. We have now a very some sort of a cosmological model which tells us that we are actually something which is not at all important for the energy density of the universe. In more detail, if you look at how much of the energy density of the observed universe is made of stuff which we are familiar with, this white ball, we are made of, this is only a very tiny fraction. A much larger fraction of the visible universe, of course these numbers vary all the time, but it's made of cold dark matter, something which we don't know what it is. The only thing which we do know it's not a standard matter particle. It's something which requires physics beyond the standard matter. And then there is an even more difficult component, which is the vacuum energy. This is something which dominates our universe, but we actually do not really know what it is. So there's a huge problem, huge conceptual problem in our understanding of the world, which is the understanding of the vacuum energy. Good. What we know, however, is that our universe is very close to the critical density, and as I said, that only like 30% of all the energy density of the universe behaves in a way which we easily understand. Good, then of course this is something I cannot really explain in a few minutes, but you can of course now look at gravity, use the Einstein equation to look at the dynamics of the universe, and after making some simplifying assumptions that there's no preferred position or direction, which is supported by observations at very large scales, you can cook down the metric of our universe to something very simple, that the only important thingy here is, the only non-trivial thing is the so-called scale factor and the curvature parameter, which controls the geometry of our space-time. So if k is positive, our space-time, two-dimensional analogon of our space has this shape, so it's like a sphere if you wish. It could be flat if k equals 0, or it could be negative curvature, so like a hyperbolic plane if curvature is negative. The only thing which is important is that there's this Hubble rate, which derives from the scale factor. And there are different types of matter in the early universe. And one, the strangest form of matter is the one that the equation of state has a minus, but this is the dominant contribution to the vacuum energy today. Good. So this is all something which I want to skip. This is just a cartoon of how our universe looked in the past. If you look at today actually it's really true that we are dominated by this vacuum energy. So of course just a cartoon. But you see that there's the energy density carried by radiation is absolutely negligible. There's some matter, and there's radiation. If you go back in time, then eventually matter will overtake. And if you go further back in time, then you are in a situation where the universe is radiation dominated. So this is roughly the picture. So you have a universe which has been radiation dominated from an early time on. We actually do not know. It could be matter dominated somewhere up here, but at an energy density or a temperature of 1 mega electron volt or so, the universe was radiation dominated. We know that from nuclear synthesis. And only later it turned out to be dominated by the other energy forms. And just now it happens to be dominated by the so-called dark energy. And of course nobody really understands why this happens just now. Good. If you look at the standard model, then you see that the particles have different mass, and they are somehow massless, or have mass below the temperature, different temperature ranges, and what you get. So I want to discuss into big detail. The only thing which I want to mention here are two things, which is the decoupling of species. So you can now track the number density of the particles, like neutrinos or photons, by just solving some basic Boltzmann equations in the early universe. And the important thing is that the universe is expanding. So what it means is there's always a competition between the interaction rates, which is something which you can certainly test in a lab or some experiment, and the expansion rate. And there are two scenarios, either this one dominates or this one dominates. If this one dominates, then this just means that the universe expands so fast that these interactions essentially never happen. At least in time scales which are relevant in this particular effort of the universe. On the other hand, if this dominates, this is something like what we would say, this is what happens today. If you do an experiment, we don't care at all about any Hubble expansion. So we have just a standard interaction. But this tells us that there's a scenario in which particle interactions can get frozen out, which means that simply this term is below the Hubble expansion. Now if you look at this term, there are two different reasons why this interaction rate can be small. So there is a thermally averaged cross-section, which is this term, and also the number of interaction partners. And there can, of course, there are two possible reasons why this can be small. Either there are simply no interaction partners, or this cross-section, thermal average of the cross-section drops down. And it turns out that both of these scenarios are, of course, realized in our early universe, and especially in neutrino physics. The first, the scenario where the interaction rate becomes, so this sigma becomes too small, is actually very relevant for the decoupling of neutrinos, which I just discussed in a sort of cartoon. We know that way below the electron scale, the neutrino interaction rate can be, neutrino interactions can be characterized by the Fermi coupling. And the interaction rate is then simply the square of the Fermi coupling, or 1 over W mass to the first power times temperature with some coefficient which I declare. On the other hand, the Hubble rate in the early universe is always given by the square root of the energy density, which is in the radiation-dominated universe just the square of the temperature times the number of degrees of freedom and so on and so forth. But what is of course very easy to see is that the slope of this function is much larger than the slope of this function, because this goes with t to the 5s and this only is 3 squared. And then for small enough t's, you will of course see that this drops below this one, and therefore neutrinos will decouple. And the neutrino decoupling temperature can be then just found by equating these two things, and we find a decoupling temperature which is of the order 1 mega electron volt, which is of course the scale of nucleosynthesis. That means you find that neutrinos start to decouple at a temperature of 1 mega electron volt. And they decouple far before the recombination of electrons and positrons, which in a certain way heat up the photons. And for that reason, the temperature of neutrinos is suppressed against the temperature of photons. There are very courageous experiments which aim at the detection of the neutrino background, which is just the detection of these valid neutrinos. And our expectation is, of course, that the temperature of these guys is below the temperature of photons, but with precisely this distribution. Of course, the word temperature in this context is both misleading, because these particles are no longer in thermal equilibrium, but they get produced in a thermal equilibrium, and therefore their thermal distribution, or their velocity distribution, is almost thermal. And therefore you can characterize the energy in terms of temperature. We have seen that there are two scenarios. One is that this thing goes down, and then there's of course the other possibility that the number of interaction partner drops, and this is what is relevant for the decoupling of photons. So there's a number density of free electrons. However, once the electrons somehow combine with the nuclei, the electrons are sort of gone. The universe gets neutral, and electrons and photons decouple. So this simply means that below a certain temperature, the number density of charged particles drops down, and you can find the more what this temperature is. But this simply means that the photons do not decouple because some reaction rate becomes too small. There's always the always have this electron interaction, never really gets suppressed. The reaction rate is always proportional to energy. In this case, what really happens is that the number, the charged particles become very sparse. And this tells us that we have a decoupling of photons, and you can find that the photons decouple at the temperature of 3 electron volt, and the universe was 300,000 years old. Good. Why am I mentioning this? This is just the very last part of my talk. I will finish very soon. I'm mentioning this because this has an interesting connection to neutrino physics. And the interesting connection to neutrino physics is simply that I want to tell you that there might be a surprise when we measure the cosmic neutrino background. So, of course, so we want, so I have one final comment, and it's just a very short comment, on the possibility of a non-thermal component to neutrino background. And this is highly connected to the nature of neutrinos. This is some option which only arises if neutrinos are general. It's the final connection. Of course, we know that, of course, there are photons coming from the sun. And we also know that neutrinos come from the sun in various experiments. We also have seen, I've just mentioned, that there are relic photons, and of course they have been measured by Penzias and Wilson and many others. Planck satellite and so on. And this is something which really gives us a huge information about the early universe. It tells us the temperature, the early history, it tells us density fluctuation, and so on and so forth. So this is something which is very measured, very understood, and highly important for our understanding of the universe. So these are the relic photons, which come really from a time when the universe became transparent. So this was somehow the surface of glass scattering, and photons scatter there, and the next time they scatter without detector. So these are the relic photons. And analogously, we could compute the flux of relic neutrinos. These are the neutrinos which decouple during the day. The question is, can we learn something from measuring those? Of course, there is the textbook expectation that they have a sort of thermal distribution where the temperature is just somewhat smaller than the temperature of the relic photons. However, we don't know that for sure. We don't have not observed these guys yet. The common knowledge is that the density of relic photons is 412 per cubic centimeters, and the number density of neutrinos is slightly below that. And it turns out that actually it could be that there are even more neutrinos than photons in our universe. That is, the most abundant species in our universe is not photons but neutrinos. This is something which could be true. And I'm just going to tell you a cartoon of how that potentially works. So this is the standard picture, which I have already explained to you. So we have, this is a cartoon of our expanding universe. So we of course assume some inflation for many reasons. The thing where we really know a lot about is this stage of Big Bang nucleosynthesis, which happened when the universe was roughly 1 second old and the temperature was roughly 1 mega electron volt. This is when the elements formed, the first elements formed, and neutrinos decoupled. And the idea, or what we expect to see, is that okay, these neutrinos decouple here and can then be here measured or observed in a very dedicated detector. It was non-trivial, but okay, this is the idea. And this contributes to this cosmic neutrino background, which is of course just the analogon of the cosmic microwave background, which gets created when the universe was 300,000 years old. And this thing is of course been observed. And we know a lot about these things. We also have a certain control over the species because there are some parameter, the effective number of light degrees of freedom, which neutrinos contribute to. And this thing has been measured. So what it in particular tells us, we cannot have tons of equilibrated so-called sterile neutrinos which add here to the freedom because this is already been observation. And the only thing which I want to mention here is that there is a possibility that if neutrinos are Dirac particles, there is a second so-called non-thermal contribution to the neutrino background. And this non-thermal contribution may even be produced during inflation. And the reason why this is in a certain way non-thermal is that these guys are never in thermal equilibrium. The right-hand neutrinos are, the neutrinos are Dirac particles, never in thermal equilibrium. And this is just related to the fact that the neutrino-Yukawa coupling is so tiny such that this interaction rate is just out of equilibrium. So these guys are never equilibrated. So this can be the standard Dirac neutrino mass from torsion. And you see that there's this Yukawa coupling, but these Yukawa couplings are small, we tend to know -12 or more. And you can check that this interaction rate compared to the Hubble rate is never close to unity. So it's here up to 10 minus whatever, 8 or so, but it's never. Good. And what that means is if we, for instance, happen to create in the very early universe of the general class of random neutrinos, they will just sit there until we may detect it. And if their energy density, if they are like very small energies at the universe, they actually do not contribute very much to the effective number of degrees of freedom, and there can be plenty of them. Even so, a bit inconsistency with all bounds on the effective number of non-distant freedoms. There are scenarios like Fermi preheating which give you that. So they are well motivated inflation scenario which will precisely produce something which looks very much like a degenerate Fermi gas in the early universe. So this is what you get. Looks rather similar. And the important point is that you can have writing neutrinos which come with a large, which can be as abundant as 270 cubic centimeter, which is like half of the number density of photons, only in the writing neutrinos, still inconsistent. People have, of course, asked whether or not one can detect valid neutrinos, and this can be done with inverse beta decay by neutrino capture. And what you really want to see is a second peak here, which you get from not just emitting neutrino but capture this inverse. Okay, you see that this neutrino energy will now add to the electron activity, and this will give you the second peak. And if you were really able to measure the second peak, then you would also be able to measure the valid neutrinos. There's even a concrete proposal for that. So this person, at least last year in LG, was still very serious about this proposal. Whether or not this will ever be built or will ever be successful, I don't know, but at least people are serious about this. And what they expect is that there's a rate of 8 to 23 events per 100 tritium and per year for higher 100 neutrinos. People then have said, well, this will also allow us to distinguish between Dirac and Majorana neutrinos. And the simple reason being is that Dirac neutrino is 50% of the time a writing neutrino, something which you mentioned the other day. That's the so-called maximal Nixon, where you be 50% right-handed. Right-handed neutrinos do not interact, and therefore are unmeasurable. Therefore, they would say that the interaction rate for Dirac neutrinos is just half of what it is for Majorana neutrinos, and this will allow us to distinguish between Dirac and Majorana neutrinos. Of course, in order to make more detailed distinctions, you have to find out what is the local identity of neutrinos. But this can be done. And what is important is that if you have this additional component, writing component, of course these additional writing neutrinos will be now today 50% left-handed or active, and they will add to the number density or to the detection. And this can completely overcompensate this factor 1/2 which you get from here. And therefore this experiment may actually not be able to distinguish between Dirac and Majorana neutrinos. This is just the last point which I wanted to make, that there have been some proposals which seemingly allow us to distinguish between Dirac and Majorana neutrinos, but you don't have to be actually too creative to find a scenario in which Dirac neutrinos mimic Majorana neutrinos. So this experiment alone, yeah.
So there have been some analysis where they basically in the cosmic microwave background they did an analysis. So some people did an analysis where they basically observe how the spectra is shifted due to the neutrino, the relic neutrinos.
Yes.
So in case of this non-thermal background, could that also produce some effect that could be?
No, what the F always, what I know is what they always essentially measure is the energy density of different epochs. This gives you the constraint on delta NF. What you essentially do is if you have additional degrees of freedom, you have more energy density in the universe, which means the Hubble rate becomes larger. And then the comparison between other rate and the nuclear interaction rates becomes different, and we create different amounts of elements and so on and so forth. You always have constraints on the effective number of massless degrees of freedom.
So that's the only effect that we can see in the CMB.
But the crucial caveat of this is that we always assume here massless degrees of freedom which have a thermal distribution.
Yeah.
So you take the energy density which they contribute under the assumption that they have a thermal distribution. However, these right-hand neutrinos have no reason whatsoever to be in a thermal distribution. They can be in a thermal gas distribution such that their contribution to the energy density is much lower than you get from an equilibrated species. And for that reason, you can have plenty of them, 200 of them, without being in contradiction to these experiments that you made. Yeah? So this is simply because they can have much lower energies, individual energies, than what you would get from a thermal distribution. And this is nothing crazy because a right-hand neutrino has no reason to be in a thermal distribution. It's never equilibrated if it's there. There's simply the interaction rate is so tiny, there's no reason to expect that this should be a thermal distribution. So that means if you do that, in a certain way you say you make a distinction between Dirac and Majorana, you don't do it because you have neglected the most important fact that the right-hand Dirac neutrino is essentially decoupled. And again, this is something you don't have to work out, it's just there. You just take the standard model Dirac neutrino coupling, 10 to the minus 12, square it, multiplied by the temperature, this gives you the interaction rate, it's tiny, it's below half. Yeah?
Yes, so I have a silly question. So the whole thing seems to be motivated for the Dirac case, with the Yukawa being so slow, so small.
Check.
And therefore it doesn't thermalize.
Absolutely.
But I could think of why is the Yukawa small at that scale?
No, you just run it and it doesn't run much. The Yukawas don't run much. They maybe run by a factor of. This Yukawa doesn't run much, but even the top Yukawa doesn't run more than a factor of. But this runs much less. The running is tiny. The running always is, of course, dictated by the interactions of the particles involved. And if the particle involved doesn't have any interaction, the running is not very pronounced. But even if they would run like a top Yukawa coupling, this wouldn't make any difference because the reaction rate is far, far below the upper limit. In fact, the bound on the Dirac-Yukawa coupling expressed in terms of a Dirac neutrino mass is more of the order of 1 kilo electron volt for coming into equilibrium. Your question is interesting in other aspect. Of course, you could have a model, like whatever left-right symmetric model with a lone left-right scale, and then these guys would be in some equilibrium as long as the left-right symmetry is there. And people have looked at such models. Yeah? And in those models, you cannot play this game unless the inflation scale is below the left-right symmetry breaking scale.
So here you're not thinking of a UV complete theory.
Well, I take the standard model.
You're just running it up. You just run it up.
Yeah. So
no unification or anything.
Well, you can do that within a supersymmetric model with their neutrinos can do
with tiny Yukawas at the unification scale.
Yes. And then you say you can say these are in principle other particles. They don't come from a 16 cut, and then you relate whatever they are smallest to something like Carantino mass or Blancas or whatever. You just say it happens to be small for one of these reasons. And what is sort of cute is that if you do that game with inflation, it turns out that actually only one degree of freedom where you can play this game, which is the right-hand neutrino. And this is simply because this is the only particle for which we can write down such a term, such a coupling to the inflaton. This is impossible because all other particles are charged, they cannot have this coupling. The only particle in a standard model with Dirac neutrinos is the right-hand neutrino. You can write down such a coupling. People did that, and what they found is essentially something like a Fermi distribution for these things because there's some parametric resonance in the decay of the electron. So it's not completely weird. Of course, this is not the simplest model of the world, absolutely not, but it's not too weird to make these assumptions. Anyway, so that's basically it. So maybe this is a good picture to stop the talk. Yeah, thank you very much. So if there are further questions.
Yeah. Thank you very much for your interesting lecture. First on, you see, for the connection of the string world with the physics below the Planck scale. In this I have a question. And second, I would like to know, I'm impressed by your thinking about relic neutrinos. And I have a question.
Sure.
I don't know, but
yeah, sure.
I start. The first is, okay, in the process of compactification, I think you mentioned the case from 6 dimensions.
No, from 10 to 4.
Yeah, okay. My question is there any remnant, any relic of the properties that you had before the compactification on the 4th dimension?
What do you mean?
For example, in terms of, for example, what we call in the description of physics in 4 dimensions, we call internal charges, for example. Could these internal charges be remnants of this process of compactification from higher dimensions?
I mean, it depends on what you mean by remnant charges. For instance, the framework which I was mostly working in is
what I call relic is that we observe, properties of the systems which are not related to a space-time, to 4-dimensional space-time.
No, sure. I mean, one prominent example is the asymmetries. I was talking about asymmetries, but asymmetries are nothing but remnants of the Lorentz symmetry of compact space. You see, you have 6 compact dimensions, and in these 6 dimensions, you could also do Lorentz transformations. Yeah? Why not? Yeah? Now, of course, if this has some freaky shape, like a tetrahedron or whatever, only a subset, a discrete subset of these Lorentz transformations are really symmetries of the model. But these things happen to be asymmetries from the 4-dimensional point of view, simply because fermions and scalars and gauge fields have different transformations properties of under the Lorentz group. So these discrete asymmetries, especially the C4R, which I was advertising here, is a discrete remnant of the Lorentz group. And this is something that you get from a C2 orbifold plane. So this was this pillow. This has this rotation symmetry by 90 degrees, and this manifests itself as a C4R symmetry.
Yeah, but these are discrete symmetries of the Lorentz groups, which are still acting on the space-time properties.
Sure.
But charge conjugation, okay, where is parity or time reversal, it has to do, but you see what we call the charges.
Yes,
okay?
Sure, and in this case it's very simple.
That in field theory in 4 dimensions appear as generators of this group.
I'm sure. But charge conjugation is always simple. I mean, the question is why is PCT at the same footing? Yeah? And the simplest way to understand this is Kaluza line where you have the circle. You get the one from the circle. If you do a reflection or parity reflection of the circle, you invert the charge. This is why P is at the same level. Yeah? And the only thing that in the heterotic string you don't have a circle, but you have a root lattice of E8 cross E8, which gives you a gauge group E8 cross E8. And charge conjugation does precisely the same. It's just a reflection of these coordinates. In fact, you have 16 left-moving string coordinates which live in this lattice, and charge conjugation is just a reflection of these. This is your charge conjugation. There's nothing strange about these. So this is what it is. And you always have a complete understanding in terms of these. And these are the internal charges. This is all unified in this set. There's no miracle.
Okay, moving to this field. Okay, your conclusion, or at least indication instead of conclusion, that may be difficult to distinguish between Dirac and Majorana, to me is a big surprise, because always I use the sentence that for non-relativistic neutrinos, which is the case of the present neutrino relic, the distinction should be very easy. I don't know.
Why is it easy?
Yeah, let me ask. Okay, if I have, or perhaps later we discuss privately on this question, because you see, the point that I'm thinking is that probably your conclusion is established in terms of what is the number density that you have in one case and the other.
No, I will have to discriminate.
But you see, on the spin properties, I think they have to be completely different.
Yes.
You see, when you produce neutrinos,
Absolutely.
you see, in the primordial universe, with definite chirality means at that time for relativistic neutrinos, definite helicity. But you see, at present times, for non-relativistic neutrinos, there is no privileged direction.
Absolutely, that's why.
Okay, that means you should have a distribution of the spin components which is completely unpolarized.
Absolutely, this
You
is
see,
where this factor
from
2.
complete polarization to
This
unpolarized.
is where this factor 2 comes from. You're absolutely right. And if you have no freaky extra component, there is a factor 2 difference in the detection rate. This is precisely what you're describing. It's completely right. And the one intuition about this is that 50% of the time a Dirac neutrino is right-handed and cannot be detected.
Yeah, but in the case of Majoron, you don't have the right-handed component.
Precisely, it's always can detect it, therefore the reaction, the detection rate is double. That's what these people made. So that's what happens. That's precisely your intuition. This is where this factor 2 comes from. And this gave the people the hope to distinguish between Dirac and Majorana with this experiment. And all I'm saying is that if they are Dirac, there can be a non-thermal component which spoils this argument. But without this non-thermal stuff, you're completely right. They're completely different. There's a factor 2 in the detection.
Yeah. On the other hand, I don't know any dynamical evolution explaining, you see, using the expansion of the universe, because it's not a boost. The expansion of the universe is not like a boost in going from high energies to low energies. You see, it's more
But we are
complicated
moving
thing.
away in a certain way from the neutrinos formula they protect, and therefore it's a redshift. There's no boost, but you see, I mean, the universe which we are seeing today, we have a huge relative velocity.
And then, to me, it's difficult. I remember, you see, the discussion with Wolfenstein many years ago on this question: what will be the Hamiltonian describing this? Without the Hamiltonian, I don't know how to go from chirality to the dynamics of the expansion. Okay, but this is another point.
Let's continue this. Any other question? No?
So, well, I just like to know that there is a way to link these two parts of your talk. The first part about, I don't know, neutrinos in string theory, and the second part in cosmology is something that might link them.
And you know very well that all our successful models predict the Majorana genders. And as of now, I have not a single complete string model which comes with the neutrinos. So this is just, disregarding all the heterotic discussion and just say, okay, maybe there's some part of the string universe where you can do the neutrinos. And this is just completely bottom up. This has no, real relation to a real complete string model that I know. All Dirac neutrino string models that I know are somehow sick, some sector.
Well, we want to thank you for a very nice evening. Our group picture, which we couldn't have yesterday because it's cold and rain, around 11 at the art. So we can have a coffee. Get out of the bed. And somebody lost the fountain. Somebody sitting over there. No.
I have
relación del neutrino con neutrinos esféricos, un modelo de Omar.
Porque Omar tenía uno, pero para la composición del dinero.
Ya le echamos números y le pegas. Está avanzado, sí.
Vamos a sacar super heavy dark matter para eficiente.
No.
Sí, es que hay
Da para algo.
Yes.
Quisiera entender de dónde sale la idea de que yo podría estar hablando con él.
Nomás debe ser la cancha de un espejo.
Ok.
Y ahí, con eso.
Eso lo explica todo.
Estaba para foto.
Si lo traes, te tomo una foto y te la mando. Perfecto, no te preocupes.
It's just that there was too much to zero.
Pero me hubiera gustado. Por ejemplo, que dio Pancho. Pero eso tanto los detalles.
Beta is like beta function.
No,
¿Qué pasó?
Muchos sentences.
Para decir para baño, ¿no? Usa para baño.
Sí.
Yes.
Everybody's here. He's the 11th shop. So, German again, that's right. Start with the Alright, so I'm just going to continue Michael's discussion, and this is the second part of the lecture on neutrinos in cosmology. Namely, I'm going to discuss baryogenesis through leptogenesis. Of course, the question, namely, the understanding of the origin of the cosmological symmetry between matter and antimatter, this remains great challenges, both in particle physics and cosmology. There are two pieces of evidence. Together they point toward the same values in terms of this symmetry. One is coming from the measurement of the cosmic microwave background anisotropy, where this anisotropy depends upon the ratio of the baryon number density to the photon number density. And therefore, by this measurement, one will be able to extract this ratio. Another piece of evidence is from Big Bang nuclear synthesis, which measure the primordial abundances of the light elements. By combining these two type of measurements, we now know that the number density of the baryon to photon is on the order of 10 to the minus 10. Right, so Sakharov, of course, already told us back in the late 60s, if we would want to generate the baryon number dynamically, there are three conditions that must be satisfied. We need a violation of baryon number. We need a violation of charge and charge parity, CD. And we also need the departure of thermal equilibrium. Within the standard model, of course, all these three conditions are already there. First of all, in the standard model, we have CP violation in the quark sector. However, it turns out that this amount of CP violation in the quark sector does not give rise to sufficient amount of baryon number symmetry. We also see that in the standard model, there exists accidental symmetries, including the individual lepton flavor numbers, and as a result, the total lepton number. It predicts massless neutrinos, and therefore there's no charged lepton flavor violations. And now, since we know neutrinos oscillate, and therefore they have non-zero masses, this indicates physics beyond the standard model, and in addition, there could exist new CP violating sources, namely the CP phases in the PM&S matrix. So neutrino masses open up this new possibility for baryogenesis, and that is through the mechanism called the leptogenesis. Alright, so the plan for this lecture is as follows. First, I will go through some basic ingredients that are needed in order to do a leptogenesis calculation of model building. And this includes the Sakharov's three conditions and also the sources of CP violation that exist in new physics beyond the standard model. Then I will move on to the standard leptogenesis. This is the vanilla version of the leptogenesis in which neutrinos are Majorana fermions. Next, I will look at a very interesting and somehow unexpected to many people, the possibility of having leptogenesis in the case of Dirac neutrinos. Namely, if lepton number is conserved, whether it is still possible to get leptogenesis. And that's under the name of Dirac leptogenesis. After this introduction, I will look at the so-called gravitino problems, which is a generic problem that is related to high-scale leptogenesis or even baryogenesis. And this motivates various non-standard scenarios, such as the so-called resonant leptogenesis, and I've already alluded to a bit, sub-leptogenesis, and non-thermal leptogenesis. And at the very end, I will conclude by discussing the possible connections between leptogenesis and low-energy CP violations that we may be able to measure in the low-energy experiments, such as neutrino oscillations. Of course, this is a big subject, and I by no means is an expert on all the area. So there are no local experts in the audience, and please feel free to jump in and offer your perspectives. All right, and this is mainly based on my past lectures a while ago, which drew a lot of materials from these three very excellent reviews on leptogenesis and baryogenesis, and in which you can also find the original references on various topics that I discussed. All right, so first Sakharov condition, baryon number violation. this type of processes, baryon number validating processes, are necessary in order for a baryon number symmetric universe to evolve into a universe with baryon number violation, not baryon number, sorry, the baryon number non-symmetric universe. And of course, in grand unified theories, as Mike already discussed, given that quarks and leptons, now they are unified in the same representations, now the quarks can morph into leptons, and therefore baryon number violating processes are very natural, and they are actually pretty abundant. And this typically through the interactions with a gauge field or the scalar field. In the standard model, both the baryon number and the lepton number appear to be accidental symmetries of the standard model. So what that means is they are preserved at the tree level. But to find out that the non-perturbable effects, namely the incidental effects, actually break these accidental symmetries in the standard model at the non-perturbable level, and more precisely, these processes violate B plus L while preserving B minus L. All right. So this is a more detail. At the point, yeah.
I still think that there is a difference in the standard model between B and L, because B at the level of the Lagrange, okay, non-perturbative effects, this is different. The Spaleron program. But you see, in the case of the standard model, you cannot write a term which is baryon number violating engaging. However, you can do it for neutrinos, violating lepton number, for example, for Majorana neutrinos. That means you have to put in the standard model lepton number conservation by hand. In the case of baryon number, it is not necessary to put by hand. There is no way of having a dimension for baryon number operating. It was always baryon number. I think there is a
so that's consistent
in the
with
standard model, I
here.
think there is a difference between B and L, okay? At the level of the Lagrange, I think. Do you agree with this comment? I mean, you see, these are accidental symmetries, but in the case of B, you see, is a mask, in the sense that you cannot write the baryon number violating term. However, in the case of lepton number, if you have it, you put by hand. This symmetry.
Right, but here I'm restricting myself in standard model, the right-handed neutrinos, and the Lagrangian is given with that particle content that.
Okay.
All right, so at the quantum level, the non-vanishing ABJ triangular anomaly, which is through the interactions with the electroweak gauge fields, are given right here. So what you can see is a divergence of the current associated with the baryon number is equal to the divergence of the current associated with the lepton numbers, and again, they are proportional to the number of families. And given that these two divergences are equal, B minus L is preserved, while B plus L is violated. So another way to look at this is that the vacuum structure of the non-abelian gauge theory, of the SO2L, is as follows. Namely, it has degenerate vacuum, or it has infinite number of degenerate vacua, and these vacua are separated by the so-called Chern-Simons numbers. So we try to settle integer numbers. And using the non-perturbable calculation, it was found that the changes in B and L are related to the changes of these topological charges, namely the Chern-Simons numbers, through this relation. And given that there are three families, delta B and delta L must be violated by 3 units of an integer number. So this leads to, so from here, one can deduce that the spheron processes, the so-called spheron processes that are due to the transition from one vacuum to another, must include 12 fermions. Because there are 3 generations, there are 3 quarks, and each quark carries 3 colors, and there are 3 leptons. So in total, it's a 12 fermions. It's a process that involves 12 fermions. And this is one of the examples of such 12 fermions processes. Of course, the rate at which such processes can take place depends on the tunneling rate from one vacuum to another. It was shown that at zero temperature, such transition rate is negligible because they are exponentially suppressed. But in thermal bath, such transition can actually take place not through the tunneling, but thermal fluctuations. And the bottom line here is at high temperature, and by high I mean temperature above the electroweak phase transition scale, such B-violating processes can be unsuppressed. Alright, so the spheron processes in thermal equilibrium, they are active, is in this range between 100 GeV up to 10 to the 12 GeV. The second set of conditions, namely the charge and charge parity violations, this can be demonstrated, I think best by using a simple example. So now let's consider we have a super heavy boson. It's called X, and it decays. It can decay through the following processes. Right, so X can decay into 2 quarks, and this process, of course, violates the baryon number by 2/3. Right, because each quark carries 1/3. And let's suppose that the branching fraction for this process is given by alpha. X can also decay into Q by L bar, and this of course violates the baryon number by -1/3. And let's suppose that these are the only 2 decay processes that X can decay into, so the branching fraction here is 1 minus alpha. There are also the conjugate processes with respect to branching fraction of alpha bar and 1 minus alpha bar. So you can do a simple calculation and ask what is the total baryon number that is being produced due to the X boson decay and the X bar decay. Right? So for example, due to the first decay, we produce 2/3 units of the baryon number with respect to branching fraction of alpha, where due to the second process, we produce a delta V of -1/3 with respect to branching fraction of 1 minus alpha. So this gives us the baryon number that is being produced by the X boson decay, which is L1 minus a3. And likewise, you can ask what is the baryon number that is being produced through the X bar decay, and this is the answer. Alright, so these are all tree level. And therefore, the total baryon number is the sum of these 2 net baryon numbers, which is given by alpha minus alpha bar. So if CP is conserved, then the 2 branching fractions, alpha and alpha bar, must be equal, and therefore there's no asymmetry, no net asymmetry that is being generated. Alright, so that's good? Alright. So now I'm going to look at the toy model, and by the way, this is actually a nice example coming out of Coben-Turner, so you've already seen it before. So using this toy model, we can look at various criteria in order for CP violation to be manifest. And in this toy model, we will introduce 2 heavy scalar fields, X and Y, and in addition, we have 4 fermions. So I'm going to label them as F sub I. And suppose this is a Lagrangian that involves a set of fields, 2 scalars and 4 fermions, and this Lagrangian leads to the following 4 possible decay processes. So X, this heavy scalar field X, can decay into F1 bar plus F2 and F3 bar plus F4. Similarly, this heavy field Y can decay into F3 bar plus F1 and F4 bar plus F2. So these are various decay processes these 2 heavy scalar fields can decay into. Right, so at the tree level, the rate of the decay of X going into F1 bar plus F2 is given by the decay coupling constant here, G1 squared, times the phase space vector, which I indicate with I sub X. All right. And likewise, the conjugate process of X bar decay into F1 plus F2 bar is given by this expression, So again, this is a conjugate, complex conjugate of G1 squared times the same phase space factor. Right. And given that these two phase space factors are equal, at the tree level there's no asymmetry. So what that means is we need to go to one loop. So in one loop, there are these two diagrams that contribute to the x decay that involve the second scalar field, y, so that you can see right here. And likewise, for the y decay, there are two one-loop diagrams that involve the scalar field x. Okay? Alright, so at the one-loop level, this x decay into f1 bar plus f2 is given by this. So this is this is the interference term between the tree level and one loop. So that interference term is given right here. This is a product of the four coupling constants times this I sub xy, which combines the phase space factor in the kinematics. Likewise, the x bar decay into f1 plus f2 bar its interference between one loop and tree level is given by this expression. Right. So the relevant quantity that we need in order to extract the asymmetry is a difference between the rate of these two conjugate pair of decay processes. And the difference is given by the emergent part of this vector Ixy times the emergent part of this product of the coupling constants. Okay. And likewise, for the other decay channel of x, likewise it is given by this expression. So put them together, this is a final result. Right? So using through the first decay channel, x decay into f1 bar plus f2, this generates a lepton number of b1 minus b2. Where the second process, x decay into f3 bar plus f4, this gives rise to a lepton number of violation of b4 minus b3. So the total asymmetry is given by this difference, the sum of these two terms divided by the total rate. Alright, so again, the asymmetry that is generated through the x decay in the final result is given by this expression, where again, to draw your attention, here are the vector Ixy, which combines the phase space factor and the kinematics, and here I have the emergent part of the product of these four coupling constants, and this is again a symmetry associated with the y decay. And of course, the total asymmetry is a sum of these two asymmetries. So if you stare at this expression, what you find is that in order to have a non-zero total asymmetry, you do need two b-violating bosons whose masses are greater than the fermions that run in the loop. Okay. Secondly, to have non-vanishing asymmetries, we do need the complex coupling constants. Otherwise, these two terms will vanish. And what this means is we do need CP violation, and this is coming from the interference between the tree diagram and the one loop diagram. Because as we see before, the one loop contributions just vanish. The third condition is that we do need non-degenerate x and y scalar field masses. Otherwise, these two factors would be equal, and again, the two contributions cancel. All right, so this is a take-home message to get CP asymmetry through a decay of the heavy particles. These are the conditions you need to satisfy. First of all, you need two non-degenerate scalar fields, and secondly, it is due to the interference between the tree level and the one loop contributions. Then of course, you do need the CP validating coupling constants. They need to be complex. Okay, so third condition, this is departure from thermal equilibrium. Yeah.
I'm sorry. Yes, in case of having just one single X field, super heavy X field,
right,
you could take also a non-zero symmetry back in a certain way. Not at all. Even at n loops.
And a loop.
At two level, it's clear.
Right, even if one loop it vanishes.
Vanishes.
May I make a comment?
Yeah.
Really, the one loop is needed only in the imaginary part, in the absorptive part. I mean, these are really unitarity corrections. In order to build the asymmetry, you need the physical imaginary part responsible of CP violation. But this is not enough. You need also another imaginary part. The reason for that is that all physical quantities are real numbers. Okay? And the other is an absorptive part. If you had particles with final state interactions, would be enough. You see, the final state interactions can generate this absorptive part. For example, when you have, okay, not in the case of these fundamental particles, but when you have a hadron, you see, with final state interaction of the decay products, is enough to generate that. That means the one loop is not essentially one loop, only the absorptive part of the loop. That
Right,
is
so-
what people call unitarity corrections. You need unitarity corrections in order to have an absorptive part.
Right, so later,
Together with the physical imaginary part.
right, so here I'm just concentrating on CP symmetry that is generated by the decay. And later, in the so-called sublithogenesis scenario, you will see that this is another way that CP symmetry can manifest, namely the CP violation through the oscillation. And that's when the both absorptive part and the distributive part will come into play. Yes.
I see the question, but the first one is just kinematic, right? I mean,
Yeah, this is kinematic. Yes, precisely. This is all coming out of kinematic. Yes. All right. Okay, departure from thermal equilibrium. So first of all, the first thing to note is that the baryon number is odd under C and CP. All right. So you take use of this if you take into consideration of this fact, together with the fact that the Hamiltonian commutes with CPT, then you can follow through and prove easily that in thermal equilibrium, the average number of baryon number vanishes. All right, so this is a result following from the fact that B is odd under C and CP, together with the fact that the Hamiltonian commute with CPT, and therefore I can move this factor around. Together using this fact, you can prove that in thermal equilibrium, baryon number vanishes. All right, so there are possible ways to achieve departure from thermal equilibriums. And this is really at the heart of what distinguishes different mechanisms for baryogenesis. So if the out of equilibrium condition is achieved through the decay of heavy particles, and this is possible because of the expansion of the universe, this is like first class models. And mechanisms that fall under this category include the so-called baryogenesis. So this is like really the very old version of baryogenesis using the decay of the heavy particles. And also, leptogenesis also fall under this category. All right. The second way that departure from thermal equilibrium can be achieved is through the electroweak phase transition. So the famous electroweak baryogenesis fall under this category. I think Miriam can tell us more about this. And therefore, I'm just going to concentrate on the first scenario, namely out of equilibrium decay of heavy particles. All right. So again, in this case, the out of equilibrium condition is achieved because of the expansion of the universe. And Michael already talked about this a little bit in his lecture. The basic idea is that here I have a super heavy particle X, whose decay rate is given by this is gamma X, and the particle has mass m sub x. At temperature, which is roughly on the order of the mass of this heavy particle, namely when you become non-relativistic, if the decay rate of this particle is smaller compared to the expansion rate of the universe, then the X cannot decay on the time scale of the expansion. and therefore it must remain in its initial thermal abundances, which scales as temperature to the third power. All right. And this abundance, of course, is larger than the thermal abundance at temperature below its mass, which is a lot more suppressed, as you can see right here. So this overabundance between the case where this heavy field fall out of equilibrium, so this is overabundance when it fall out of equilibrium compared to its expected abundance in equilibrium. This is the signatures of the departure from thermal equilibrium, and this is the third condition that is necessary in order to generate a final non-vanishing baryon number symmetry. So when I look at this ratio, comparing the decay rate of this heavy particle to the expansion rate of the universe, this is inverse proportional to the mass of this heavy particle. So what that means is, in order to achieve the out of equilibrium condition, we need the heavy particles. If the decay of this heavy particle is through the renormalizable operators, one can derive a sort of a general bound. If this particle is a gauge boson, then mx must be very close to the gas scale, 10 to the 15 to 16 GeV at least, in order for its decay to be out of equilibrium. Where if the decay particle is a scalar field, then the bound is somewhat more relaxed. It's between 10 to the 10 to 10 to the 16 GeV. And of course, the precise, to do a precise prediction and see whether the decay is really out of equilibrium by considering the various washout processes, this would require a precise computations using the Boltzmann's equations. Yeah?
Were you just via the normalizable operator?
Not necessarily. So this is just the calculation. I mean, in order to derive this bound, this bound only apply when the operators are renormalizable. And I'm not going to talk about the non-renormalizable operator. All right? So that's a condition for this bound to be valid. All right. So another ingredient which is needed in order to perform a lipogenesis calculation is a relation between delta B and delta L. So at high temperature symmetric phase of the standard model, this is a weakly coupled plasma, one can assign the chemical potential to each fermions and also the scalar fields in the plasma. And given that there are n sub f generations of fermions, there's 3 generations, but you can go beyond, and there's 1 Higgs, in total there are 5 NF plus 1 chemical potentials. So I'm not going through the detail, but just to draw, just to give you some punchline. The number density, in this case, the number densities of the particles in the plasma are related to the chemical potentials. Yes, and using the fact that various processes are in thermal equilibrium, now we can derive various relationships among these chemical potentials. So this allows us to express the baryon asymmetry and lepton asymmetry in terms of just the chemical potentials. And therefore, you get a relationship between these 2 asymmetries. So I'm skipping a lot of steps, but the key point here is that each species of particles will have a chemical potentials. And then you can ask, at this temperature range of interest, what are the processes that are in equilibrium? And therefore, that give rise to constraints among various chemical potentials. And make use of that and the fact that you can write number densities in terms of the chemical potentials. The final result is, you can then get a relationship between delta B and delta L. And that relationship is given in terms of this factor that I call C sub S, which is in the presence of n sub F generations of fermions and n sub H Higgses. All right, so that coefficient is given right here, and I will make use of that later. All right. So yes, as I said, there are various mechanisms that exist already for a long time for baryogenesis. In gap baryogenesis, there's a single particle physics interaction at some high temperature, and this is given by the great unified theory, where the baryon number violating processes are very natural, because quarks and leptons are in the same multiplates, and there exists super heavy gauge boson mediated baryon number changing processes. The charge and charge parity violations are also very naturally built into these theories. And the out of equilibrium condition is met because the Gauss effects take place at very early time, and given the cosmic expansion is much faster compared to the gauge interactions, the decays of these heavy particles are intrinsically out of equilibrium.
Sorry, maybe I just missed it. What do you mean with gut effects?
These are all gut interactions. Right, such as SU5 or SO10.
But are they out of equilibrium?
They are out of equilibrium if these heavy particles are heavy enough. Right, but so the whole point here is, in the gut theory, this gut baryogenesis can be implemented because you have all the ingredients there. No? All right? But there, of course, also exists quite a few challenges for gut baryogenesis. First of all, you require very high reheating temperatures after the inflation. And this leads to dangerous production of the relic, and the so-called gravitino overproduction problem, which I will go into more detail later. Given that all these interactions take place at the gas scale, it is extremely hard to test with low energy experiments, such as those at the colliders. And furthermore, the electroweak theory violates baryon number and can erase any pre-existing asymmetry, unless the gas model you consider can generate an excess in the Beeman cell number. So this sort of prefer SO10 gas theory over SU5, right? Because SU5 doesn't contain Beeman cell as a subgroup. Just very briefly, for electroweak baryogenesis, here the out of equilibrium condition is provided by strong first order phase transition. And of course, it is attractive to many people because there is a hope of testing electroweak baryogenesis at the collider. But it also has various problems. First of all, it requires more CP violation than what is being provided in the standard model. It needs strong enough first order phase transition. And this condition generally is in conflict with the observed Higgs mass.
So is everything you're talking about in supersymmetry, or are there remarks that talk about supersymmetry are in addition to what is always true? Like for example, you said the gravitino problem before only happens in supersymmetry, but the rest is general, or you always talk about SUSY gas?
No, just general. So
because the gravitino problem obviously is not a problem.
Oh, sure. So gravitino problem, that's specific for SUSY. Right. But yes. So that's a part you're asking? Or?
So yeah. So if not mentioned otherwise, it's general, and if it's something that has to do with supersymmetry, then it has to do with
precisely.
Okay.
Yes. Thank you for the clarification. Yes.
Sir, in that particular case, when you mentioned the gravitino problem, you might have some other relic instead of the gravitino in a
No. You produce too many gravitinos.
No. Let's forget about supersymmetry. Let's suppose that the model is not supersymmetric. Could you have another relic in that particular case? In the previous slide? There.
Right. So I think in this case, no. This is specific for SUSY.
This is only supersymmetric. Okay.
Right. Right. Thanks. All right. So here you need going back to electroweak baryogenesis. This requires much lighter Higgs mass compared to the observed 126 GeV Higgs, and therefore, in the most simple setup, electroweak baryogenesis.
What do you mean by too many? Maybe it can help to explain that matter, right?
What do you mean? What are you
When you say that after inflation you can produce too many gravitinos. It depends on the mass of the gravitino, but it can solve the problem of that matter, in principle, as well. Instead of having a problem, you can solve a problem.
Right, so I will show you the two like constraints for the two cases. One is when gravitino is LSP, and therefore it could be a dark matter candidate, and there's, again, some additional constraints. Okay, so yes, I will talk about that later. Any other comments before I go? All right. So the very last ingredients concern the sources of CP violation. So in the standard model, CP is not an exact symmetry in the weak interaction, and we of course have the evidences from the K-on and the meson systems. And of course, this CP violation is manifest in the complex space in the CK matrix. And again, I'm not going through this. I think you have seen this already in particle physics lecture. So CK matrix for three families, it is a unitary matrix that include it's 3 by 3 unitary matrix involving three families. It contains 3 mixing angles and 1 phase because you can absorb 5 out of the 6 phases by Gilbert definitions. So an estimate shows that the CP phase in the CK matrix actually gives rise to a baryon number of symmetries that is way smaller compared to the observed value, which is 10 to the minus 10. So of course, going beyond standard model, the next candidate is MSSM. And in MSSM, you already acquire, or there already exists, quite a few additional CP balloting sources because of the increasing in the number of coupling constants that you have. In particular, these new CP balloting sources are coming from the self-SUSY breaking parameters. All right. So here I show the superpotential of the MSSM that include the new terms and various Yukawa couplings, where the parameters in the self-SUSY breaking sector include the following set. We have the trilinear couplings, the bilinear couplings, the B term, the gauginal masses, and the soft-scalar masses. If you concern yourself in the constraint MSSM with M2 ground mediation, in total, there are only 2 physical phases in the self-SUSY parameters. So these are the 2 additional CP phases that exist in the constraint MSSM. And these are the relative phase between the trilinear A term and the gauginal mass. These are the arguments of these products and the phase of the B term. All right, so here you have 2 additional phases coming from self-SUSY breaking part of the MSSM. All right, so a third possibility to get new CP phase is, this is possible because of the non-zero mass of the neutrinos. So we already seen this before. This is, of course, the major goal of the current research of various experiments. And if you found it, that leads to very, could have important implications for baryogenesis. Yeah.
So before you go to the lepton sector, I suppose there is a theta term in guts. And is there any study whether that could provide enough CP violation?
So I mean the GG deal for the
That's right, yeah.
I'm not aware of. I don't know whether. Right, but he's talking about the state-out term equivalence.
Yeah, the equivalent.
Right?
So you say that it would be washed out?
But the gap biogenesis has usually this washout property. Minus A0 and the washout minus energy by this
I don't know how that get implemented.
Okay.
But we can talk more about that later. I'm not aware of
these things will always, I think, conserve E minus L. So you will always have a B plus asymmetry, which will just get washed out. Unless you do something. So even if the block.
Well, we can talk about that more later. All right, so now let me get back to the lepton sector, right? The Lagrangian and the high energy in the presence of three right-handed neutrinos generically are given in this form. So here I have the kinetic terms and and the Yukawa interactions for the charged leptons, for the neutrinos, and the Majorana mass terms for the right-handed neutrinos. And here I just concern myself with three right-handed neutrinos. So in the basis, where the charged lepton mass matrix and the right-handed neutrino Majorana mass matrix are diagonal, and I'm not losing any generality here because I have the degrees of freedom to rotate to this basis. Hij, this is the Yukawa coupling for the neutrino-Dirac interactions, is a general complex matrix. Right, so this is a 3 by 3 general complex matrix which contains 6 mixing angles and 6 physical phases. But now, after I integrate out 3 right-handed neutrinos, this is remaining effective low energy Lagrangian. So once again, I can go to the basis where the charged lepton mass matrix is diagonal, and the Hij, which is the left-handed Majorana mass term for the light neutrinos, is in this case symmetric and complex. So this contains 3 mixing angles and 3 physical phases, because it's Majorana, that restrict the number of rephasing degrees of freedom I have. So the lessons here is that when going from high energy to low energy, the number of mixing angles and CP phases are reduced by half. And this, of course, would have implications when we try to establish the connections between leptogenesis and low energy experimental observable. So this will come back later. Right? All right, so now I'm going to leptogenesis. So again, this is the most general Lagrangian in the lepton sector, and as Mike already told us, if MR is heavy enough, and MR typically is very close to the Gus scale, and if I have, let's see, what is my notation here? Right. So if I assume this MD is on the order of the electroweak scale, this is natural. Then you can solve this 2 by 2 type 1 seesaw matrix and obtain that you have a heavy mass eigenstate, which consists mostly the right-handed neutrino, and its mass is close to MR, with active neutrino state, which is a mixture of the two, and its mass is highly suppressed by the ratio of the electroweak scale to the Gus scale. All right. So the basic idea of lithogenesis is that now you have the out of equilibrium decay of the right-handed neutrino, which gives rise to lepton number symmetry. And at the lower scale, these spheron processes then convert this lepton number asymmetry into the baryon number asymmetry. All right. So the CP asymmetry due to the right-handed heavy right-handed neutrino decay arises due to the interference between the tree label, namely the right-handed neutrino decays into charged leptons and Higgs, with the one loop contributions. And at the one loop, there are 2 pieces of contributions. One is through the vertex correction that involve another species of the right-handed neutrinos in the loop. And the second type of one loop diagrams is this. So this, right, the self-energy diagram. And given that this is exactly the same coupling constants as the Dirac interactions of the neutrinos, the neutrino-Yukawa couplings, this is what allows you to possibly establish the connections between leptogenesis and low energy oscillation parameters. Of course, later you will see the connection may not exist at all. But this is what leads to a lot of excitement about this possibility. Right. So the total asymmetry due to the right-handed neutrino decay is given by the difference between the right-handed neutrino decays into leptons plus the Higgs and the conjugate decays of the right-handed neutrinos into the anti-leptons, right? So if there's CP violation, then these two decay rates would be different, and this would then give you the non-zero asymmetry in the end. All right, said that already. So if you look at it more closely, the two type of diagrams give you these two pieces of contribution. All right, so here, again, I should just tell you the total decay width of the right-handed neutrinos depends on the Yukawa couplings in this form, and is proportional to the right-handed neutrino mass. And so this is the exact calculation will give you where the this function f is corresponding to the vertex correction contribution, which I will show in more detail what it looks like. And the second piece here is due to the self-energy diagrams. Okay. Right. So again, vertex correction and the wave function renormalization. So the bottom line here is that if you have hierarchical right-handed neutrino masses, then the vertex correction dominates, where you can basically ignore the wave function renormalization contribution. However, so this is then the final result. But if you have near degenerate right-handed neutrinos, if these two right-handed neutrinos have near degenerate masses, then the wave function renormalization becomes important, and this leads to the so-called resonant leptogenesis. So, yes, and this could, in principle, be an alternative of leptogenesis in order to solve the gravitino overreduction problem. All right. So, first, this asymmetry that gets generated could be washed out by various processes. And this is where the out of equilibrium condition comes in, right? So out of equilibrium condition require that the decay rates of the right-handed neutrinos to be smaller compared to the expansion rate of the universe. And you can put in, the expression that we just saw. This ratio is inverse proportional to the right-handed neutrino mass. And by requiring that this ratio to be smaller than 1, you can actually set a constraint on this combination of the neutrino coupling constants, the Yukawa coupling constant. So what this is basically telling you is the effective mass of the neutrino, which is given by this combination, must be smaller compared to 10 to the minus 3 electron volt. All right. So this is the asymmetry that we saw before, and kappa here, this basically tells us how much washout effects there are. If it's totally out of equilibrium, kappa of course here is 1. You don't lose any asymmetry. But in order to know precisely how much washout there is, you need to solve the Boltzmann's equation and really calculate what the this efficiency factor is. Very good. Right, and another ingredient that you need is to convert this amount of lepton asymmetry to the baryon number asymmetry. And that's where the chemical potential discussion come in. So again, through this, through that chemical potential argument, we know how to relate the lepton number asymmetry to the baryon number asymmetry. And this is the total final baryon number asymmetry that you obtain. Right, so I think I can just, right, so here to show you possible processes that can wash out the asymmetry that get generated. This include the decay, the inverse decay of the right-handed neutrinos. There's also the 2-to-2 scattering. Some of them violate Lepton number by 1 unit. So here just give you some example of the 2-to-2 scattering that leads to Lepton number violation by 1 unit. And oops, some of the processes violate the Lepton number by 2 units. So again, these are a set of 2-to-2 scattering processes that could wash out the asymmetry that was generated. And to properly know the amount of asymmetry that get generated, you need to put all these processes into the Boltzmann equations and solve for the number density and see what remains. All right. So the bottom line is, if you ask what would be the constraints on the neutrino parameters in order to generate sufficient amount of baryon number symmetry that leads to the constraints on the mass of the lattice right-handed neutrinos to be greater than 10 to the 9 GeV. All right, so now I'm going to come to the question, namely, is leptogenesis possible without Lepton number violation? Right. Meaning, if neutrinos are Dirac, whether we can still implement leptogenesis. And the answer is yes, and this was discovered by Michael in his master's thesis, bachelor's thesis. Leptogenesis is possible even if neutrinos are Dirac. And it is possible due to the following characteristics of the spheron processes. And knowing that the small Dirac neutrino masses are coming from the highly suppressed Yukawa coupling on the order of 10 to the minus 12. So the important characteristics of the spheron processes are the following. First of all, the spheron processes, the spheron effects only couple to the left-handed fields, not the right-handed fields, because only the left-handed fields they interact through SU2L. Secondly, spherons change B plus L, but not B minus L. So we also seen that earlier. And the third aspect or third characteristic is that the spheron effects are in equilibrium. They are active at temperature above the electroweak phase transition scale. So the basic idea is that if somehow we can create some asymmetry, Lepton number asymmetry, that gets stored in the right-handed fermions, which do not talk to the spherons, and this asymmetry can survive below the electroweak phase transition after the spheron processes shut off, then net Lepton number asymmetry can be generated, even though we started out with vanishing total Lepton number. Right? So I think a cartoon picture would illustrate this better. So if I have Dirac neutrinos, total Lepton number would be 0, right? Because delta L equals 2 doesn't exist. Right? So there's no delta L equals 2 violation. So total Lepton number here is preserved. If somehow we have certain mechanism that can generate some asymmetry that gets stored in the right-handed sector, and given that there's no total Lepton number violation, you should have corresponding delta L but with opposite sign that gets stored in the left-handed sector. That's an equal amount of asymmetry in the left-handed sector and right-handed sector. They are equal amount but in opposite sign, and therefore total Lepton number is conserved. So that's the first step. But now the spherons are active, so it converts it converts the Lepton number into the baryon number, right? Because this is B plus L violating. But the right-handed Lepton number is unaffected because they don't talk to the spherons. And now after the spheron process is shut off, that's when the Left-right equilibration come into sorry, let me say it this way. The Left-right equilibration happens only after the spheron shuts off. So even though there's Left-right equilibration, that doesn't wash out the baryon number and Lepton number asymmetry that you generated. And therefore, you could have a remaining non-zero baryon number asymmetry. So the question is, what would be the condition on the Yukawa coupling, or equivalently, the fermion mass, in order to achieve this late-time equilibration? Okay. So neutrino Yukawa couplings, here it is. The rate of Left-right conversion is proportional to the coupling constant square and the temperature. For this Left-right conversion not to be in equilibrium, you have to compare this conversion rate to the Hubble constant, which scales as temperature squared. So by this requirement that Left-right equilibration occur at a later time, later meaning below the electroweak phase transition, you obtain this constraint, namely the coupling constant has to be smaller compared to 10 to the minus 8 or minus 9. And this is equivalent of saying that the particle mass has to be smaller than 10 keV. And therefore, neutrinos, due to their small Yukawa couplings, this late-time equilibration condition indeed is satisfied. Okay. All right. So once again, because of this left-right equilibration of the neutrinos, this makes Dirac leptogenesis possible, even if you start off with a zero primordial Lepton number asymmetry. All right. So now I'm coming to the gravitational overproduction problems. So again, just to remind you, in order to have sufficient leptogenesis, this requires the right-handed neutrino mass to be greater than 10 to the 9 GeV. This leads to an upper bound on the light neutrino mass, which is of course consistent with the current experimental data. But if you look at the absolute mass, this is somehow incompatible with the quasi-degenerate neutrino mass spectrum. All right. So these right-handed neutrinos are produced thermally. This constraint then leads to a constraint on the reheating temperature, which has to be greater than 10 to the 9 GeV. But the number density of the gravitinos, this scales with the reheating temperature. So with this high reheating temperature, it leads to an overproduction of the light state, the gravitinos. So if gravitinos are the LSP, like Eduardo wanted to suggest, right, so that they can be dark matter candidates, you have the dark matter constraints from W map, and this could lead to strong bounds on the Brunino mass for any given gravitino mass and the reheating temperature. But if gravitinos are unstable, of course in this case they are not the dark matter candidates, they could then decay during or after the BBN, and there are various effects on the BBN. So first of all, you could speed up the cosmic expansion, and the gravitino can also decay radioactively and therefore change this ratio of baryon number to photon number densities. But most importantly, there's the photo-dissociated reactions, which I listed here. This could destroy the light elements and therefore leads to inconsistency with the predictions from BBN. So you can turn this around by using the observed abundances of these light elements and place the constraints on the gravitino number density. And what you find is the following. So the bottom line here is the light gravitational mass in this region, the reheating temperatures reheating temperature has to be smaller than 10 to the 5 to 6 GeV, which of course leads to great tension with the requirement coming from sufficient lipogenesis, sufficient thermolipogenesis. And again, this is only applied if there's supersymmetry. Alright, so this motivates this gravitational overproduction problem leads to various proposals of the non-standard scenarios. Basically, the question is how do you alleviate this tension coming from the requirement of sufficient symmetry for lipogenesis and this gravitational overproduction. And to avoid these tensions, there are various ways. One is through the resonant enhancement in the self-energy diagram that I showed you. And this can occur if the right-handed neutrinos are near degenerate. And again, just to remind you, CP violation is this type of mechanism. We need standard type lipogenesis through right-handed neutrino decays. This is CP violation of decay. You can also relax the relations between the lepton number symmetry and right-handed neutrino mass. And that is the so-called self-leptogenesis, which is making use of these two additional CP phases that I showed earlier coming from the self-Susy breaking parameters. Right? And again here, CP violation, instead of coming from decay, this is due to the oscillation. So it's a bit like KK bar oscillation. It's exactly the same formulation that goes through. The third way to relax this tension is to relax the relationship between the reheating temperature and right-handed neutrino mass. And of course, this is only possible if the right-handed neutrinos are produced non-thermally. So this is the so-called non-thermal leptogenesis, which in some models can be connected to the inverton. So I mean, the way that right-handed neutrinos are generated, it could be through the decay of the invertons. I'll just skip all these details, but coming to the very last topics, namely whether it is possible to test the idea of leptogenesis. So once again, in order to test leptogenesis, you need to, So the bottom line is it is not possible to have a direct test of leptogenesis. But nevertheless, we could have archaeological evidences, and what I mean, and this is coined the phrase from Hitoshi Murayama. And what this means is that we could have evidences of all the ingredients that are needed for leptogenesis, right? Even though there's no direct proof. So the first second condition, out of equilibrium, again, we have the evidence of the expanding universe. So this is what it needs to implement leptogenesis, especially in this vanilla type leptogenesis with Majorana neutrinos. But the smallness of the neutrino mass also leads to the possibility of Dirac leptogenesis, and this is due to the late equilibration temperature that is below the entropy phase transition temperature. The second condition, namely the baryon and lepton number violation, is of course abound in many extensions of the standard model. And for lepton number violation, of course, that depends on whether neutrinos are Majorana or Dirac. And one important experiment that can tell us, and maybe the only experiment that can tell us, is a neutrinoless double beta decay. So if you have the scenario of leptogenesis with Majorana neutrinos, then we should have a signal, or neutrinoless double beta decay should take place, even though we may not be able to observe it. But if it's Dirac, I don't know whether there's any way to confirm that neutrinos are Dirac. So that's still a challenging problem. And of course, from cosmology, if neutrinos are Dirac fermions, this non-thermal components of the right-handed neutrinos may have additional interactions, and that could increase or change the energy factor. So there might be some, depending on, so this model dependent, but this additional radiation may give us some hope by probing precisely the energy factor through cosmology. And the third condition, namely the CP violation, of course, this is the goal of the long baseline neutrino experiments, and we may be able to observe it in hopefully near future. All right. So just to come back to this parameter counting that we did earlier, remember the seesaw Lagrangian at very high energy in the presence of 3 neutrinos. It contains 6 mixing angles and 6 physical phases. Where at the low energy, after integrating out the 3 right-handed neutrinos, we have 3 mixing angles and 3 physical phases remaining. So given that going from high energy to low energy, the numbers of mixing angles and CP phases are reduced by half. Generally, there is no connection between leptogenesis and the presence of low energy CP violation. All right. So again, there's no model independent connection, meaning if you observe, say, CP violation in neutrino oscillation, that doesn't mean that there's leptogenesis. And conversely, even if the Dirac CP phase vanishes, you could still have successful standard leptogenesis because you have this additional phases of high energy. So I think this is pretty important to appreciate. Right? No model independent connections. But certain predictive models, connections can actually be established. So I'll come to that in just a minute. But even model independently, depending on the spectrums of the right-handed neutrino masses, the so-called flavor effects may be important. All right, so the so-called flavor effects, this has to do with the fact that the different charged lepton Yukawas, they equilibrate at different temperatures. So if the lightest right-handed neutrinos has its mass on the order of 10 to the 12 GeVs, at this temperature, the tau flavor is in equilibrium, while the electron and mu flavors are not. But if leptogenesis takes place at a lower scale, say 10 to the 9 GeV, then those tau and mu flavors are in equilibrium, but the electron flavors is not. So if you somehow in these 2 flavor regimes, then you need to track the tau flavor, or the asymmetry associated with the tau flavor, and the other 2 flavor independently. Where the statement, where the formulation that I showed you earlier actually sum up the asymmetries associated with all the 3 flavors. Right, so maybe I have it. Right, so this expression here, actually sum up all the 3 different flavors, sum up the asymmetries associated with 3 different charged leptons flavors. Also, if you take into account these flavor effects, then you can show that in order to have non-zero leptogenesis, you do require low energy CP violations. So this really depends on at what scale that leptogenesis takes place.
Sorry,
Yeah.
this should be Dirac, or it can be...
No, this is
Majorana.
referring to Majorana, the standard, the decay of the right-handed neutrinos. Yes, so only apply to
No,
standard.
but the CP violation at low energies.
Oh, The CP violation
Is for
in general.
both
In
Dirac and
general.
Majorana, or
Yeah, in general here.
so it's considering both?
In both.
Okay.
Right, so the idea is that here you really have the individual elements in the PMNS matrix that doesn't get, get somehow
The
absorbed.
absolute.
Right, absorbed. Right, right. Very good. So even without considering the flavor effects in specific models, you can already, it is possible to establish such connections between low energy CP violation and leptogenesis. And typically these models have the following structures or following characteristics that make it possible to establish such connections. So those models could have additional symmetries like what we've heard so far, quite a lot, and therefore that leads to reduction of the number of parameters. And that's the whole idea of why such connections is possible. Here just give you some example. For example, it was proposed that if there are only 2 right-handed neutrinos, then you would have a rank 2 mass matrix, and this could be realized by certain symmetry, and there are existing models where this can be realized. And in this specific case, the sign of the baryon number symmetry actually get related to the sign of CP violation, the sign of CP violation in neutrino oscillations. Another possibility is to have all these CP violation coming from a single source. So for example, if you have models with spontaneous CP violation, there may only be the phase of the relative phase between the scalar fields that is dictating all the CP violation phenomena in the model. And in such case, you can also establish the connection. So example, it could, here are specific models where there's only one single phase that is controlling all these CP violation processes.
Both for leptons and quarks?
Yeah. So I think this particular model that works for both leptons and quarks. And some of the models you may need 2 phases. One working in the lepton sector, the other working in the quark sector. Right? But that's very model dependent. But I think the general takeaway message is that if you just have a single source for CP violation, then naturally you could make such connection. Okay. So I think I just come to my conclusion. The original matter is still a great mystery in the particle physics and cosmology. Leptogenesis, this is an appealing mechanism that may make connections to the neutrino physics. There are various leptogenesis realizations. There is standard leptogenesis, which in supersymmetric case suffer from the gravitino overproduction problem, so there's a tension. There are various low-scale alternatives to alleviate such tension. And of course, leptogenesis can occur even if there's no primordial lepton number violation. To test leptogenesis, this is impossible directly, but we could have various archaeological evidences. So we talk about the various, ways that these archaeological evidences can appear, and model dependently, if you have a very restricted model for neutrino masses, one can also hope for establishing this connection between low energy experiment and the baryon number symmetry, where the mechanism of that generation could take place at a very high energy scale. So I'll stop here.
Are there any questions? No questions? She can ask you. There's no single question she can ask you, because that's the rule. So just pick one and ask.
Put again the transparency of the one-loop diagram.
Oh.
We didn't come to this question of that particular.
The one with that. diagonal?
Yes. That means that you need the interference between the 3 level and 1 loop. Yeah. You see, suppose that instead of putting a specific diagrams, you put, you see, this is a particular decay channel. That you put that the initial particle has a total explicit. That means, what I'm talking about the sorting part is that cutting the 2 loop diagrams at the level of the loop, okay? You cut, okay? And then it's like putting an absorptive part, the width, the total width.
Right.
I have the feeling that automatically then you have a non-vanishing effect, including, because the total width will include this particular diagrams at the level of 1 loop. Yeah, because if I remember right, in K range, what you need is an interference, you see, of different amplitudes with different CP phases and different, okay, call strong phases, unitarity correction. That means, you see, phases that are coming from the fact that in general the amplitudes are complex, not related to the phases of CP variation. That means, my point is, you see, I remember that everybody is putting these loop diagrams and so on. Okay, then you generate the effect. But as simple as, let us call initial state interaction, that means you cut these 2 loops. Okay? And then it's equivalent to say that if you sum over all absorptive corrections in the unitarity relation, then you correspond to put explicitly that the initial state has a total decay. That means you put the propagation with Joseph. You know,
but I think that's not
like
sufficient.
when you have a propagator putting explicitly the total loop, that means there is an imaginary part which corresponds to the absorptive. I have the feeling that in the calculation then automatically you will generate the effect.
So that's not
only putting the absorptive part.
You can get these diagrams by cutting to propagate.
Yeah, put in the
So,
propagator. What I mean,
it's known that
but in the
eventually
denominator of the propagator you put explicitly the total loop. Also, that means it's a complex propagator.
Sure, but it's also known that these imaginary parts come from the real part and the things go unshred. This is well known.
There's a firm
cross-beam cutting. This you can apply here, but the result is the same.
Right.
Okay,
And that's not the only
I
part.
will check. I will.
Right, so the fermions here must be unshelved so that that factor in that co-example I show you, what I call IXY, they include the base factor kinematics. That part is complex because the loop fermions are unshelved. So that's correspond to what you said, but that's not, you also need the complex
You
complex
see, when you put, apart from the CP phase in the 3 level you cannot generate because you see the amplitude is real.
Right.
Except the phase, it doesn't matter. If you put the square, it doesn't matter whether you put the phase, the CP phase or not. The modulus square, you don't see it.
Sure.
Okay? You need to put another component that means that the amplitudes are complex. You see, it's the T matrix, it's not the board amplitude. Okay, anyway,
So
this is something that I will check because historically, in fact, I will tell Cecilia also because in the early 80s we were the first to say that in decay rate you needed something else in order to generate.
Right. So it's consistent with this. Yes.
At some point in your talk, you mentioned topological charges. Can you explain a little bit more about it? Because I didn't understand it.
So this is an instant line effect. I think they are better expert than me to. Right, just because of the structure of the vacuum of the non-abelian gauge theories. Yeah.
Can you comment more on the phasor effects when you go to low energy
Low energy photogenesis.
low, but they go
Right, so if you go further down, 10 to the 9, that's 2 flavor regimes, right? And furthermore, below 10 to the 7, you are in 3 flavor regimes. So you really have to track the asymmetry associated with electron flavor, the muon flavor, and Hall flavor independently. and then add them up. And that's the total asymmetry. Instead of relying on the standard result that I showed there. Right.
More questions or comments? No? So, today, so
Tomorrow, so we have the.
so you have still a few more minutes. You don't have to just ask the questions. Yeah, keep going.
No, pero yo creo que
Bueno, lo que voy a hacer es, pero tengo que coger todos los... Bueno,
then you have to worry about the next one. The next one can be a guy with a strong correlation. Such that these guys are essentially
donde tomamos un break, el café, ¿en cuántos minutos? 10 minutos.
Ja, das ist leider minutos.
A la 1:15.
Mixing and there's an exchange.
A la 1:10 donde el break.
So there is
A la 1:10 donde el break. A la 1:10 donde el break. Thank you very much.
This can happen, but I don't like the setting.
A ver, ¿quieres comer aquí lo que estás diciendo?
Parameters where you surround it by werden die
Sí, va a haber alguien. Sí, te estoy diciendo que tú no vas a llevar.
we have checked it.
Como chofer me quedo. Puedes quedar No, pues vamos. Y si Carles no tiene compromiso, pues ya me llevo. Ni modo, lo invitamos. O te llevas a tu familia.
¿Sabes cuántos vamos?
Miriam, ¿dónde?
10 aquí, donde tomamos el café.
1:10, okay. 10:10 where we have the coffee.
Ahorita voy por mi hijo.
We all gather.
Si me da tiempo, regreso. Mi lugar puede ser ocupado por Arturo Micha. Ya le voy a... No es que me lo contan.
Si me da tiempo. So then he puts the implicos friends and once he's